Welcome to Triune Biblical University Global Extension USA channel. A warm welcome to all our returning subscribers and a heartfelt greeting to our new viewers. We're so glad to have you with us today. Whether you've been following us for a while or are just joining the community, we're excited to embark on this learning journey together. At Triune Biblical University Global Extension USA, we strive to provide valuable educational content that empowers you to grow, learn, and succeed. Your continued support and participation mean the world to us. In today's session, we are diving into lecture topic, where we'll explore important concepts and provide practical knowledge that you can apply in real-world scenarios. This lecture is designed to challenge your thinking and deepen your understanding, whether you're a beginner or an advanced learner. Thank you for joining us, and we hope you find today's lecture both insightful and inspiring. Let's get started. Before us today is an interesting lecture topic tagged Advanced Geotechnical Engineering. Sit back, relax, and enjoy. Chapter 1: Introduction to Advanced Geotechnical Engineering. 1.1 Overview of Geotechnical Engineering. Geotechnical engineering is a specialized field of civil engineering that focuses on the study and application of soil and rock mechanics to the design, construction, and maintenance of infrastructure projects. It plays a crucial role in the planning and execution of projects such as roads, bridges, buildings, dams, tunnels, and foundations, all of which are deeply influenced by the properties of the underlying ground. The primary objective of geotechnical engineering is to ensure the stability, safety, and sustainability of structures and systems by understanding how soil and rock interact with these structures under various loading conditions. Geotechnical engineers are responsible for assessing the physical properties of the ground, designing appropriate foundations, and mitigating risks such as settlement, slope instability, and soil liquefaction. Key areas of geotechnical engineering. 1. Soil mechanics. Soil mechanics forms the foundation of geotechnical engineering, dealing with the study of soil behavior under different conditions, including stress, strain, and moisture content. Understanding soil's physical and mechanical properties such as its cohesion, friction angle, and compressibility is essential for designing safe and cost-effective foundations. 2. Rock mechanics. Similar to soil mechanics, rock mechanics focuses on the study of rock behavior and its mechanical properties. It is especially critical in projects involving tunneling, mining, and the construction of structures in areas with hard rock foundations. 3. Foundation engineering. Foundation engineering is a key subfield involving the design and construction of foundations for buildings, bridges, and other infrastructure. This includes both shallow foundations, like spread footings and slab-on-grade, and deep foundations, like piles and drilled shafts. Proper foundation design requires knowledge of soil bearing capacity, settlement behavior, and the effects of environmental factors. 4. Site investigation and characterization. Before beginning any project, geotechnical engineers must conduct thorough site investigations to determine the properties of the soil and rock on the site. This involves drilling boreholes, performing laboratory tests, and conducting field tests, such as the Standard Penetration Test (SPT) and Cone Penetration Test (CPT). The data collected guides the design process and helps mitigate potential risks associated with foundation design. 5. Slope stability and landslides. The study of slope stability is critical in regions with steep terrain or where large earthworks, such as embankments or cuttings, are involved. Geotechnical engineers analyze the forces acting on soil slopes to determine their stability and assess the potential for landslides or other failures. Techniques such as slope reinforcement or excavation stabilization are employed to manage risks. 6. Geotechnical earthquake engineering. Geotechnical earthquake engineering examines the impact of seismic forces on soil structure interaction, focusing on topics like soil liquefaction, seismic site response, and the design of foundations for earthquake-prone areas. The goal is to minimize the damage to structures and infrastructure during seismic events. 7. Groundwater and soil structure interaction. Groundwater conditions greatly ECT soil properties and, consequently, the design of foundations and other geotechnical systems. Geotechnical engineers must account for groundwater flow, seepage, and hydrostatic pressures when designing foundations and underground structures. Additionally, understanding soil structure interaction is essential for assessing how the surrounding soil will ECT the performance of the structure over time. Modern challenges in geotechnical engineering. The field of geotechnical engineering continues to evolve due to advancements in material science, numerical modeling, and testing methods. Some of the contemporary challenges and innovations in geotechnical engineering include urbanization and sustainable design. With rapid urbanization, geotechnical engineers are increasingly tasked with working in densely populated areas, requiring innovative approaches to minimize the impact on existing structures and utilities, while meeting the growing demand for new infrastructure. Climate change and groundwater management. As climate change impacts weather patterns, geotechnical engineers must consider how fluctuating groundwater levels, increased rainfall, and rising sea levels will ECT soil properties and the stability of foundations and slopes. Technological advancements. The integration of advanced technologies like geosynthetics, ground improvement techniques, and real-time monitoring systems is revolutionizing geotechnical practice. These technologies are more efficient, sustainable, and cost-effective solutions to geotechnical problems. Seismic and geoenvironmental engineering. As the global population grows and infrastructure extends into seismically active areas, understanding the interaction between soil, rock, and structures under seismic loading has become more important than ever. Furthermore, geoenvironmental concerns, such as the remediation of contaminated soils, are gaining attention within the field. In the context of advanced geotechnical engineering, we go beyond the fundamental principles and techniques to tackle these complex issues, incorporating cutting-edge tools, methodologies, and research to address the challenges of modern infrastructure projects. This book will provide in-depth knowledge of advanced geotechnical topics and explore how these developments are reshaping the industry. 1.2 Historical development and evolution of geotechnical practices. The history of geotechnical engineering is deeply rooted in human civilization's efforts to construct durable structures and foundations. Over the centuries, the field has evolved from rudimentary practices to a highly specialized discipline underpinned by scientific principles, advanced testing methods, and computational modeling. Understanding the historical development of geotechnical engineering helps illuminate the advances in both theory and practice that have shaped the discipline. Ancient foundations and early practices. The roots of geotechnical engineering date back to ancient civilizations, where basic principles of soil and foundation design were intuitively applied. 1. Ancient Egypt and Mesopotamia. The Egyptians, around 4000 BC, were some of the earliest builders to rely on principles of foundation engineering to construct monumental structures like the pyramids. They used large stone foundations to distribute the weight of the heavy stone blocks over the soft, sandy soil. While they lacked a formal understanding of soil mechanics, the results of their trial and error were effective in creating stable structures that have stood the test of time. 2. Ancient Greece and Rome. The Romans made significant advancements in engineering, especially in the construction of roads, aqueducts, and buildings that required careful attention to soil stability. Roman engineers, such as Vitruvius, recognized the importance of solid foundations, and their use of crushed stone, lime, and concrete marked an early understanding of material properties. Roman techniques influenced the development of engineering practices in Europe for centuries. 3. Middle Ages. During the medieval period, advances in geotechnical engineering were limited, but the construction of castles, bridges, and fortifications relied heavily on intuition regarding soil stability and foundation design. Early engineers were often trial and error practitioners who relied on local knowledge and experience rather than scientific principles. The birth of modern geotechnical engineering. The formalization of geotechnical engineering as a distinct branch of civil engineering occurred in the 19th and early 20th centuries, driven by industrialization, urbanization, and the need for more reliable and systematic approaches to foundation design. 1. Early soil mechanics, the 18th and 19th centuries. In the 18th century, there were growing efforts to understand the physical properties of soils. This period saw the development of the first rudimentary principles of soil mechanics, although the understanding of soil behavior was still in its infancy. 2. Sir George Everest and the study of soil pressure, 1830s. Sir George Everest, a British Surveyor General of India, made early contributions to the understanding of soil and foundation behavior in the 1830s, particularly related to the pressure exerted by soils on foundations. His work would later influence the development of soil-bearing capacity concepts. 3. Charles Augustin de Coulomb, 1773. Coulomb's work laid the foundation for modern earth pressure theory. He developed a theoretical understanding of soil's shear strength and its response to external loading, which would become a fundamental concept in geotechnical design. His equation for determining the earth pressure on retaining walls was a significant early contribution to soil mechanics. 4. The birth of soil mechanics, the early 20th century. In the early 20th century, with the Industrial Revolution creating an increasing need for infrastructure development, engineers sought more scientific ways to design foundations and assess soil behavior. This era saw the emergence of soil mechanics as a recognized scientific discipline. O. Carl Terzaghi, 1883 to 1963, often referred to as the father of modern soil mechanics, made groundbreaking contributions to the field. He developed the theory of consolidation and was the first to systematically analyze soil behavior under stress. His work on the ejective stress principle, which recognizes the role of both pore water pressure and soil particle stress in determining the strength and deformation of soils, was revolutionary. His book, Erdbaumechanik, 1925, became the cornerstone for soil mechanics as a discipline. O. Arthur Casagrande, a student of Terzaghi, contributed to the development of soil testing methods, including the Atterberg limits and the consolidation test. These early efforts in soil testing formed the foundation for the development of laboratory and field testing methods used in geotechnical engineering today. The evolution of geotechnical engineering in the 20th century. 1. Standardization and formalization of methods, 1920s to 1960s. Following Terzaghi's work, the 20th century saw significant progress in the field of geotechnical engineering, with the standardization of soil testing methods and the adoption of analytical tools for foundation design. In the 1930s and 1940s, Standardized tests, such as the Standard Penetration Test (SPT), were introduced, allowing engineers to assess soil strength and density at various depths. The introduction of theoretical models, like the Rankine and Coulomb earth pressure theories, helped engineers calculate the stability of slopes and retaining walls under different loading conditions. 2. Post-war advances in geotechnical engineering. After World War II, rapid urbanization and the demand for large-scale infrastructure projects led to the development of more sophisticated methods for geotechnical design. The introduction of the finite element method, FEM, in the 1950s and 1960s revolutionized the ability to model soil structure interaction and simulate the behavior of complex geotechnical systems. 3. Soil structure interaction and geotechnical earthquake engineering, 1970s. Present. With the increasing frequency of large-scale construction projects and the growing understanding of the importance of geotechnical earthquake engineering, the field expanded to include the study of seismic forces and their impact on soil and structures. The study of soil structure interaction gained prominence, with engineers developing models to understand how buildings, bridges, and other structures interact with the ground during seismic events. Advances in soil liquefaction research and the design of earthquake resistant foundations were made to protect structures in seismically active regions. 4. Technological advances in the late 20th and 21st centuries. The late 20th and early 21st centuries brought remarkable innovations in geotechnical engineering. Geosynthetics. The introduction of geosynthetics in the 1980s provided engineers with new materials for reinforcing soil, improving drainage, and controlling erosion. These materials became essential for modern geotechnical projects, especially in areas involving soft soils and weak foundation conditions. Geotechnical instrumentation. Advances in sensors and monitoring technologies have allowed for real-time data collection and analysis of soil behavior, helping engineers make informed decisions during construction and over the life of the structure. Computer modeling and simulation. Modern computing power has revolutionized the ability to perform complex simulations, such as finite element modeling, to predict soil behavior under various loading conditions. This has enabled engineers to design more efficient and cost-effective geotechnical systems. Recent trends and future directions. 1. Sustainability and resilience. The need for sustainable and resilient infrastructure is more critical than ever. Geotechnical engineering is at the forefront of efforts to address climate change and environmental challenges. For example, new methods for mitigating soil contamination, improving soil stabilization, and designing foundations to withstand Extreme weather events are all essential for the future of geotechnical engineering. 2. Smart geotechnics. The integration of smart technologies, such as sensor networks and automation, is shaping the future of geotechnical practice. These innovations enable real-time monitoring of soil conditions, structural health, and foundation performance, improving safety and efficiency on projects. 3. Geotechnical engineering for complex environments. As cities continue to grow, geotechnical engineers are increasingly working in complex environments, such as dense urban areas, offshore regions, and regions with challenging soil conditions like expansive clays or permafrost. The development of new techniques and materials will continue to play a key role in addressing these unique challenges. In conclusion, the history of geotechnical engineering reflects the discipline's gradual evolution from intuitive practice to a scientifically grounded field. As technology advances and new challenges arise, the role of geotechnical engineers will remain critical in shaping the infrastructure of the future. 1.3 Importance and challenges in modern geotechnics. Geotechnical engineering is a cornerstone of civil engineering, critical to the design, construction, and sustainability of nearly every infrastructure project. From roads and bridges to skyscrapers, dams, tunnels, and foundations, geotechnical engineers ensure that these structures are safe, stable, and resilient. As urbanization accelerates and infrastructure demands grow globally, the importance of geotechnical engineering continues to increase, but so do the challenges that accompany these complex projects. This section explores the importance of geotechnics in modern construction and highlights some of the significant challenges that engineers face today, as well as emerging trends and innovations that are helping to address these issues. Importance of modern geotechnics. 1. Foundations of infrastructure. Nearly all man-made structures depend on geotechnical engineering to ensure their stability. Foundations are one of the most critical elements of construction, and the behavior of the soil or rock under these foundations directly influences the safety, performance, and longevity of the structure. Proper geotechnical assessments and designs are essential for preventing foundation failures such as settlement, tilting, or cracking. Ensuring buildings, bridges, and other structures are stable under various loading conditions, e.g., dead load, live load, wind, and seismic loads. Managing geotechnical aspects of underground structures such as tunnels, basements, and parking garages. 2. Geotechnical risk management. Geotechnical engineers are tasked with identifying, assessing, and mitigating risks associated with soil behavior, groundwater conditions, and natural disasters such as landslides, earthquakes, and flooding. Effective risk management strategies are necessary to reduce the potential for catastrophic failures and to avoid costly damage during or after construction. 3. Site investigation and characterization. A key component of modern geotechnics is the ability to assess a site thoroughly before construction begins. This includes detailed soil and rock investigations using techniques like drilling, sampling, and various in-situ tests, e.g. standard penetration test, cone penetration test. Site investigation is critical for determining the strength, compressibility, and behavior of soils under load. Identifying potential geohazards such as liquefaction, expansive soils, and soft ground. Developing cost-effective and suitable foundation solutions based on accurate subsurface data. 4. Geotechnics and sustainable development. In an era of heightened environmental awareness, geotechnical engineering plays a crucial role in sustainable construction practices. By understanding and working with local soil conditions, geotechnical engineers can reduce the environmental impact of construction by selecting eco-friendly materials and construction methods. Incorporate ground improvement techniques that can enhance the properties of problematic soils, e.g., soft clays or expansive soils, making them suitable for construction. Contribute to the design of infrastructure that is more energy efficient and resilient to environmental changes. 5. Climate change and resilience. Climate change presents a growing challenge to geotechnical engineering with its potential to alter groundwater levels, soil conditions, and the occurrence of extreme weather events, e.g. floods, heat waves, storms. Geotechnical engineers must consider these changing conditions in their designs to ensure that infrastructure remains resilient over time. This includes designing foundations and earthworks that can withstand the impacts of rising sea levels, shifting groundwater tables, and more intense rainfall. Challenges in modern geotechnics. 1. Urbanization and land use constraints. As cities expand, geotechnical engineers are increasingly tasked with working in densely populated urban environments. Challenges in these areas include limited space for construction. Urban areas often have limited space for excavation and ground improvement techniques, requiring innovative and compact solutions. Proximity to existing infrastructure. Projects may need to account for the impact on adjacent buildings, roads, utilities, and transportation systems, requiring careful analysis and specialized foundation systems. Soil contamination. The presence of contaminants in the soil, e.g., heavy metals, hydrocarbons, can complicate both construction and remediation. EORTS. Addressing environmental issues such as site cleanup and containment is a significant concern. 2. Complex soil structure interaction. The behavior of soil in relation to a structure is highly complex and depends on factors such as soil type, moisture content, stress distribution, and the type of loads applied. Some of the challenges engineers face in this area include dynamic loads, infrastructure projects, especially those in seismically active areas, must account for dynamic loads due to earthquakes, wind, and TRA-IC. Understanding the interaction between the soil and structure under dynamic loading conditions requires advanced modeling techniques and simulations. Settlement and deformation, predicting and managing the settlement of foundations, especially in soft or loose soils, remains a challenge. Excessive settlement can lead to structural damage and serviceability issues. Soil structure resonance. In certain conditions, the frequency of vibrations from structures can match the natural frequency of the soil, potentially leading to amplification of movements and resulting in damage to both the structure and the foundation. 3. Expansive and soft soils. Soils with high clay content, such as expansive soils, present significant challenges for geotechnical engineers due to their tendency to swell when wet and shrink when dry. In addition to expansive soils, soft soils, e.g., peats, silts, and organic soils, have low shear strength and are highly compressible, leading to foundation failure or excessive settlement. Foundations built on expansive or soft soils are at risk of experiencing significant settlement or tilting due to changes in moisture content or loading. Costly ground improvement. Soft soils often require expensive ground improvement techniques such as deep soil mixing, vibrocompaction, or the installation of deep foundations like piles or piers to ensure stability and prevent settlement. 4. Seismic design and liquefaction. Earthquake-induced soil liquefaction is one of the most significant geotechnical hazards in regions with loose, saturated sands. During an earthquake, liquefaction can cause the soil to lose its strength and behave like a liquid, resulting in lateral spreading, movement of the ground causing severe damage to structures and infrastructure. Foundation failure. Structures may experience tilting or collapse due to the loss of support from the soil. Ground displacement. Earthquakes can cause ground deformation that affects both the built environment and the underlying soils, requiring the implementation of complex mitigation measures, such as soil stabilization or deep foundation systems. 5. Technological advancements and data management. Modern geotechnical projects often generate large amounts of data from soil tests, sensors, and real-time monitoring systems. One of the challenges facing the field is actively managing and interpreting this data to make informed decisions. Some areas where technology is transforming geotechnics include Real-time monitoring, advances in instrumentation and sensor technology allow for continuous monitoring of soil behavior and structure performance. However, processing and interpreting large datasets remain a challenge. Finite element modeling, numerical modeling, such as the finite element method, FEM, has become an essential tool for simulating soil structure. Interactions. While these tools provide powerful insights, they require a high level of expertise and computational resources to use effectively. 6. Cost and time constraints. Geotechnical engineering often requires careful planning, extensive testing, and site investigations, which can be both time-consuming and costly. However, modern projects frequently face tight budgets and schedules. Balancing these constraints while ensuring safety and structural integrity is an ongoing challenge for geotechnical engineers. Emerging trends and solutions. Despite these challenges, significant advancements are being made in the field of geotechnical engineering. Advanced soil testing and characterization. New methods of testing, such as the use of digital imaging, high-resolution geophysical surveys, and advanced laboratory techniques, are helping engineers better understand soil properties and improve design accuracy. Ground improvement technologies. Techniques such as ground freezing, soil stabilization, and deep soil mixing are improving the ability to strengthen weak soils and make them more suitable for construction. Sustainable geotechnics. Innovations in sustainable construction practices, such as the use of recycled materials, geosynthetics, and low-carbon footprint designs, are helping mitigate the environmental impact of geotechnical projects. Smart geotechnical systems. The integration of smart sensors and data analytics in geotechnical engineering is revolutionizing the way engineers monitor and manage projects in real time. These innovations owe solutions for improving safety, reducing maintenance costs, and enhancing the longevity of infrastructure. In conclusion, geotechnical engineering is more crucial than ever in shaping the built environment. The challenges posed by modern urbanization, climate change, and complex soil conditions demand innovative solutions. As new technologies and techniques continue to emerge, the field of geotechnical engineering will continue to evolve, meeting the demands of a rapidly changing world. 1.4 Scope of Advanced Geotechnical Engineering. Advanced geotechnical engineering represents the forefront of the geotechnical field, focusing on complex and specialized challenges that go beyond traditional practices. As infrastructure grows in complexity and scale, the need for innovative, reliable, and sustainable solutions becomes critical. Advanced geotechnical engineering encompasses a wide range of topics, methodologies, and technologies designed to address these challenges in an increasingly demanding built environment. This section outlines the scope of advanced geotechnical engineering, covering both the theoretical foundations and the practical applications in modern engineering projects. 1.4.1 Core Areas of Advanced Geotechnical Engineering. 1. Soil and rock mechanics. Soil and rock mechanics is the cornerstone of advanced geotechnical engineering. Understanding the behavior of soils and rocks under various loading conditions, including static and dynamic loads, is essential for designing foundations and other structures. This area includes soil structure interaction, SSI, the study of how soil and structures interact when subjected to loads. Advanced modeling techniques such as finite element analysis, FEA, help simulate and predict the behavior of structures on complex soil systems. Stress and strain analysis of soils, investigating how soils deform and react under stress, including elasticity, plasticity, and time-dependent behavior, is fundamental in predicting settlement and stability. Critical state soil mechanics, a more recent development in soil mechanics that focuses on understanding the failure and stability of soils based on their current state rather than their past history. 2. Ground improvement techniques. Ground improvement involves modifying the properties of problematic soils to make them more suitable for construction. In advanced geotechnical engineering, new and innovative methods are used to stabilize weak soils and improve their engineering properties. These include soil stabilization. Techniques such as deep mixing, cement stabilization, and chemical grouting are used to enhance soil strength and reduce settlement in soft soils. Vibrocompaction and dynamic compaction, methods that densify loose sands or silts by applying vibratory or dynamic forces to increase the soil's strength and bearing capacity. Geosynthetics, the use of synthetic materials such as geotextiles, geogrids, and geomembranes to reinforce and stabilize soils, improve drainage, and control erosion. 3. Advanced foundation engineering. Advanced foundation engineering focuses on designing and constructing foundations that meet the specific requirements of challenging site conditions. This includes deep foundations, the design and construction of pile foundations, drilled shafts, and caissons to support heavy loads in weak or compressible soils. Shallow foundations on complex soils. Innovations in shallow foundation. Designed for sites with complex soil profiles, such as foundations on expansive soils or in areas with high groundwater levels. Innovative foundation systems. New materials and techniques, including the use of composite foundations, hybrid systems combining deep and shallow foundations, and the application of advanced materials like ultra high-performance concrete. 4. Geotechnical Earthquake Engineering. Geotechnical earthquake engineering deals with the effects of seismic activity on soils and structures. This subfield plays a crucial role in mitigating earthquake-related hazards and ensuring the safety of infrastructure in seismically active regions. Key topics include soil liquefaction, the study of how saturated, loose, fine-grained soils can lose strength and behave like a liquid during an earthquake, leading to foundation failure, lateral spreading, and surface settlement. Seismic site response, the analysis of how derived soils amplify or attenuate seismic waves and the subsequent EECT on the performance of structures. Seismic design of foundations, the development of foundation systems that can withstand seismic loads, including seismic retrofitting techniques to improve the resilience of existing structures. 5. Slope stability and landslide engineering. Slope stability is a critical concern in regions with mountainous terrain or steep embankments. Advanced geotechnical engineering techniques are used to assess and mitigate the risk of slope failure and landslides. This includes stability analysis, the application of sophisticated numerical methods, and limit equilibrium analysis to evaluate slope stability under various conditions, including the ECT of water, seismic forces, and loading. Landslide risk management, techniques for assessing landslide risk and designing mitigation measures such as soil nailing, rock bolts, and geotechnical reinforcements to stabilize slopes. Environmental factors, considering the impact of climate change, rainfall, and human activities on slope stability is a key consideration in modern slope engineering. 6. Geotechnical data collection and monitoring. The collection, analysis, and interpretation of geotechnical data are essential for designing and monitoring large-scale infrastructure projects. Modern techniques in this area include site investigation techniques, advanced drilling and sampling methods, as well as in situ testing techniques, e.g., cone penetration testing. Pressure meter testing are used to gather accurate data on soil conditions and behavior. Geotechnical instrumentation, the use of sensors and monitoring systems to measure soil properties, groundwater levels, settlement, and stress in real time, allowing engineers to make data-driven decisions during and after construction. Geophysical surveys, techniques like seismic refraction, electrical resistivity tomography, and ground-penetrating radar, GPR, are used to obtain information about subsurface conditions without the need for invasive methods. 7. Geoenvironmental engineering. Geoenvironmental engineering addresses the interaction between soil and contaminants. This subfield involves designing solutions for contaminated sites, waste disposal, and remediation efforts. Key areas of focus include soil contamination and remediation, the assessment and remediation of contaminated sites through techniques such as bioremediation, chemical oxidation, and soil vapor extraction. Landfills and waste containment, the design of landfills, containment systems, and barriers to control leachate and gas emissions, as well as the monitoring of waste sites. Environmental geotechnics, the study of how environmental factors, including groundwater movement, soil compaction, and temperature, ECT, the behavior of soils and engineered systems. 8. Tunneling and underground construction, the construction of tunnels and underground spaces presents unique geotechnical challenges due to complex subsurface conditions. This area of advanced geotechnical engineering focuses on tunnel design and excavation, methods for safely designing and excavating tunnels, including techniques such as the tunnel boring machine (TBM) and the new Austrian tunneling method (NATM). Ground support systems, the design of support systems such as rock bolts, shotcrete, and steel linings to stabilize tunnel excavations in challenging geological conditions. Underground space utilization, the design of underground facilities such as transportation systems, utility tunnels, and storage spaces, considering factors such as soil structure interaction, groundwater control, and ventilation. 9. Advanced computational methods and geotechnical modeling with the increasing availability of computational power. Advanced geotechnical engineering now involves sophisticated numerical modeling and simulations. These techniques allow engineers to predict soil behavior and optimize design solutions. Key aspects include finite element analysis, FEA, the use of FEA to model the behavior of soil structure systems under various loading conditions, such as dynamic, seismic, or thermal loading. Discrete element modeling, DM, techniques for simulating the behavior of granular materials, including soil and rock, to predict failure mechanisms. Soil structure interaction and compaction processes. Geotechnical risk assessment, using advanced computational tools to assess risks related to soil behavior, structural stability, and environmental impacts, enabling engineers to make informed decisions during design and construction. 1.4.2 Emerging trends in advanced geotechnical engineering. As the field of geotechnical engineering continues to evolve, new trends and technologies are emerging to address the challenges of modern infrastructure. These include 1. Sustainability and green construction. The increasing focus on sustainability in construction has led to the development of green geotechnical solutions. This includes the use of sustainable materials, reducing the carbon footprint of construction projects, and adopting environmentally friendly ground improvement techniques. 2. Automation and smart technologies. Automation, robotics, and the use of smart technologies in construction processes are becoming more prevalent in geotechnical engineering. Drones for site surveying, robotic drilling equipment, and automated monitoring systems are revolutionizing the field by improving safety, efficiency, and accuracy. 3. Artificial intelligence and machine learning. Artificial intelligence, AI, and machine learning, ML, are being integrated into geotechnical engineering to enhance data analysis, predictive modeling, and decision-making. These technologies help analyze large datasets, predict soil behavior under different conditions, and optimize designs for improved performance and cost efficiency. In summary, the scope of advanced geotechnical engineering is broad and continuously evolving. It covers a diverse range of specialized topics that play a crucial role in the design, construction, and maintenance of infrastructure in challenging and complex environments. As technology advances and new challenges arise, the field of advanced geotechnical engineering will continue to grow, offering innovative solutions to meet the demands of modern infrastructure projects. 1.5 Key terminology and concepts. In advanced geotechnical engineering, understanding the specialized terminology and concepts is crucial to effectively communicate, design, and solve the challenges that engineers face. This section provides a detailed overview of key terms and concepts that form the foundation of the field. 1.5.1 Soil properties and behavior. 1. Shear strength. Shear strength refers to the ability of soil to resist deformation or failure when subjected to shear forces. It is a critical property for assessing the stability of foundations, slopes, and other geotechnical structures. The primary components of shear strength are cohesion. See the internal resistance of soil particles to separation, primarily in clays. Friction angle, by the resistance to sliding between soil particles, predominantly in sands and gravels. 2. Compaction. Compaction is the process of reducing the volume of air within a soil mass by applying mechanical energy, thereby increasing the soil's density and strength. Proper compaction is essential for ensuring adequate foundation support and minimizing settlement. 3. Consolidation. Consolidation refers to the process of gradual reduction in the volume of saturated soil due to the expulsion of pore water under a sustained load. This is particularly important for clay soils, which can undergo significant settlement over time under the influence of external loads. 4. Permeability. Permeability is a measure of a soil's ability to transmit water. It is a vital parameter for assessing drainage, groundwater flow, and the stability of structures like dams, embankments, and foundations built on saturated soils. 5. Plasticity. Plasticity is the ability of a soil to deform without cracking or breaking. It is a characteristic of fine-grained soils, such as clay, and its measurement through the Plasticity Index (PI) is essential for evaluating soil behavior under varying moisture conditions. 6. Grain size distribution. Grain size distribution describes the relative proportions of different particle sizes in a soil sample, typically categorized into clay, silt, sand, and gravel. This distribution impacts the soil's strength, permeability, and stability. 1.5.2 Soil structure interaction. 1. Bearing capacity. Bearing capacity refers to the maximum load that a soil can support before it experiences failure or excessive settlement. This is a crucial parameter for designing foundations, and the ultimate bearing capacity must be calculated for safe structural design. 2. Settlement. Settlement is the vertical downward movement of the ground due to the application of load. It can be classified into immediate settlement occurs quickly after load application, primarily due to elastic deformation of the soil. Consolidation settlement takes place over time as water is expelled from saturated soils, leading to a reduction in volume and further displacement. Creep, the slow, time-dependent deformation that occurs under sustained load, particularly in fine-grained soils. 3. Soil structure interaction (SSI). Soil structure interaction describes the mutual influence between soil and the structures built upon or within it. It involves the response of the soil to loads applied by structures and the impact of soil properties, e.g., steepness, strength on the performance of the structure. 4. Dynamic soil properties. Dynamic soil properties, including dynamic shear modulus and damping ratio, are important when assessing soil behavior under dynamic loading conditions such as earthquakes, machine vibrations, or icy loads. 1.5.3 Ground improvement and reinforcement techniques. 1. Soil stabilization. Soil stabilization involves modifying the properties of soil to improve its strength, reduce compressibility, and enhance its behavior under loading. Techniques include cement stabilization, adding cement to soils to improve strength and reduce permeability. Chemical grouting, injecting chemical solutions to strengthen and waterproof soils. Geosynthetics, using synthetic materials like geotextiles or geogrids to reinforce soil and improve its load-bearing capacity. 2. Vibrocompaction. Vibrocompaction is a technique that uses vibration to densify loose granular soils, increasing their strength and reducing settlement potential. It is commonly used in areas with loose sand or silty soils to improve the ground for foundation support. 3. Dynamic compaction. Dynamic compaction involves dropping a heavy weight onto the ground surface to compact loose soils and reduce their compressibility. This method is particularly useful for improving the bearing capacity of soft soils. 4. Deep soil mixing. Deep soil mixing is a technique used to improve weak or soft soils by mixing them with cement or other stabilizing agents to create a stronger material. This process is often used in foundations and earthworks. 1.5.4 Geotechnical Design Concepts. 1. Factor of safety FOSS. The factor of safety is the ratio of the soil's ultimate capacity resisting forces to the applied loads. A factor of safety greater than 1 ensures that the soil can safely support the structure without failure. It is commonly used in slope stability, foundation design, and other geotechnical analysis. 2. Limit state design. Limit state design is a method used in geotechnical engineering to design foundations and structures to ensure they remain safe under both normal and extreme loading conditions. The design considers both serviceability limits, e.g., acceptable settlement, and ultimate strength limits, e.g., the point of failure. 3. Settlement control. Settlement control refers to the design strategies used to minimize the movement of the ground beneath a structure. Methods include choosing appropriate foundation types, e.g., piles versus shallow foundations, improving soil properties, e.g., through ground improvement techniques, and managing load distribution. 4. Load transfer mechanisms. Load transfer mechanisms refer to how loads applied to a structure are transferred to the underlying soil. These mechanisms are critical when designing foundations and involve understanding the soil's response to applied loads, such as how shear stresses and bearing stresses are distributed. 1.5.5 Seismic and earthquake engineering concepts. 1. Liquefaction. Liquefaction is a phenomenon in which saturated, loose, granular soils lose their shear strength and behave like a liquid under the influence of seismic or dynamic loading. This can lead to severe ground deformations, foundation settlement, and structural failure during an earthquake. 2. Seismic site response. Seismic site response is the behavior of soil during an earthquake and how it influences the amplification or attenuation of seismic waves. The soil's properties, such as steepness and damping, significantly ECT the ground shaking experienced by structures. 3. Dynamic loading. Dynamic loading refers to the application of loads that vary with time, such as those caused by earthquakes, machinery, or TRA-IC. Understanding how soils respond to Dynamic loading is essential for ensuring the stability of foundations and structures. During such events, 1.5.6 Geotechnical Engineering Tools and Technologies. 1. Finite Element Analysis (FEA). FEA is a numerical technique used to simulate and analyze the behavior of soils and structures under various loading conditions. This method breaks down complex geotechnical problems into simpler elements, providing engineers with detailed insights into the soil-structure interaction and helping optimize design solutions. 2. Geotechnical instrumentation. Geotechnical instrumentation involves the use of various tools and devices to measure and monitor soil properties, groundwater levels, deformation, and other critical parameters during construction and throughout the life cycle of a structure. These tools provide real-time data for better decision-making. 3. Cone Penetration Test (CPT). The Cone Penetration Test (CPT) is an in-situ test used to determine the properties of soil by pushing a cone-shaped probe into the ground. The data collected, including resistance to penetration and sleeve friction, help engineers assess soil strength and stratigraphy. 4. Geophysical methods. Geophysical methods, such as seismic refraction, resistivity tomography, and ground-penetrating radar (GPR), are non-invasive techniques used to investigate subsurface conditions. These methods provide valuable information about the soil and rock layers, helping engineers design safer and more efficient foundations. In summary, the key terminology and concepts outlined in this section form the basis of advanced geotechnical engineering practice. A deep understanding of these terms allows engineers to address the complex challenges associated with soil behavior foundation design, ground improvement, and seismic analysis, ultimately leading to safer, more reliable infrastructure. Chapter 2: Soil Mechanics Revisited. 2.1 Soil Structure and Composition. Soil is a complex and heterogeneous material that plays a vital role in geotechnical engineering. Understanding its structure and composition is essential for assessing its behavior under various loading conditions, as well as for designing foundations, slopes, and other geotechnical structures. This section revisits the fundamental concepts of soil structure and composition, with a focus on how these factors influence soil behavior and performance. 2.1.1 Soil Composition. Soil is primarily composed of four major components. 1. Mineral particles. Clay, fine-grained particles, typically smaller than 0.002 millimeters in diameter. Clays are cohesive and of significant plasticity, making them susceptible to shrinkage and swelling. They also exhibit high compressibility. Silt, slightly larger than clay, with particle sizes between 0.002 millimeters and 0.075 mm. Silts are often less cohesive than clays, but still show a degree of plasticity and can retain water. They have moderate compressibility. Sand, coarse particles with sizes ranging from 0.075 millimeters to 4.75 millimeters. Sands are non-cohesive, with high permeability and relatively low compressibility. They provide good drainage and stability for foundations. Gravel, larger particles, ranging from 4.75 millimeters to 75 millimeters. Gravel is highly permeable and exhibits low compressibility, often providing excellent bearing capacity and drainage. 2. Water in soil exists in various forms. Free water, water that fills the voids between soil particles and is not chemically bound to the particles. Capillary water, water that adheres to soil particles due to surface tension, filling the spaces in the capillary zone, pores between particles. Hygroscopic water, water that is chemically bound to the soil particles and is typically not available for plant use or movement. 3. Air. The air component of soil fills the remaining voids not occupied by water. The amount of air present in soil is highly dependent on the soil's degree of saturation. The ratio of air to water in the pore spaces influences the soil's permeability, compressibility, and strength. 4. Organic matter. Organic materials, such as decomposed plant and animal matter, can be present in soil, especially in peaty or organic-rich soils. Organic content can ECT the soil's properties by increasing its plasticity, reducing its strength, and altering its permeability. 2.1.2 Soil structure. Soil structure refers to the arrangement of soil particles and the voids between them. It plays a crucial role in determining how the soil will behave under load, including its strength, compressibility, and permeability. Soil structure can be classified into the following categories. 1. Particle arrangement and packing. Granular soils. Sands and gravels. Granular soils are typically characterized by loosely packed or well-graded particles. The arrangement of particles in these soils allows for relatively large voids, which contributes to their high permeability and lower compressibility. Cohesive soils. Clays and silts. Cohesive soils have smaller particles that are packed more tightly. The particles are often bound together by cohesive forces, electrostatic and van der Waals forces, leading to low permeability and higher compressibility. Well-graded soils. Well-graded soils have a uniform distribution of particle sizes. These soils have fewer voids, leading to better compaction, greater strength, and less settlement. Poorly graded soils. Poorly graded soils consist of mostly one particle size, often leading to high void ratios, poor compaction, and reduced strength. 2. Soil fabric and clay particle orientation. The fabric of a soil refers to the arrangement and orientation of its particles and the bonds between them. In cohesive soils, the orientation of clay particles influences the soil's overall behavior. When clay particles are aligned or oriented in certain ways, they can significantly impact the soil's shear strength, plasticity, and volume change behavior. Clays typically exhibit a flocculated structure, disordered orientation, or dispersed structure, ordered alignment of particles, which affects their load-bearing capacity. And settlement characteristics. 3. Pore structure. The pore structure refers to the arrangement of voids or spaces between soil particles. The size, shape, and connectivity of these pores are critical in determining the soil's permeability and drainage capacity. Soils with larger pores tend to have higher permeability, while those with smaller pores retain water more effectively. The degree of saturation also influences the behavior of the soil, as the volume of air and water in the voids can affect the soil's shear strength, compressibility, and consolidation characteristics. 2.1.3 Soil Classification Systems. Soils can be classified based on their composition and structure, which provides valuable insights into their engineering behavior. Several classification systems are commonly used in geotechnical engineering. 1. Unified Soil Classification System USCS. The USCS classifies soils into groups based on their grain size and plasticity characteristics. The primary divisions are O sands, S granular soils with a particle size between 0.075 mm and 4.75 mm. O silts, M fine-grained soils with particle sizes between 0.002 mm and 0.075 mm. O clays, C cohesive soils with particle sizes smaller than 0.002 mm. O gravels, G coarse granular soils with particles larger than 4.75 mm. Each of these groups is further divided into subgroups based on the soil-specific characteristics, such as plasticity or gradation. 2. ASHTO Soil Classification System developed by the American Association of State Highway and Transportation Officials, ASHTO. This system is primarily used for road and highway construction. Soils are classified into groups based on their particle size distribution and plasticity, with emphasis on their suitability for highway. Subgrades. 3. Atterberg limits. The Atterberg limits are used to classify fine-grained soils, primarily clays, based on their moisture content and plasticity. The primary limits are O liquid limit, LL the water content at which the soil changes from a plastic state to a liquid state. O plastic limit, PL the water content at which the soil changes from a semi-solid to a plastic state. O. Plasticity index. Pi, the difference between the liquid limit and the plastic limit, which is an indicator of the soil's plasticity. 2.1.4 Soil behavior and response to loading. The structure and composition of soil influence its behavior when subjected to various types of loads. Key aspects include 1. Elastic and plastic deformation. O. Elastic deformation. When a load is applied to a soil, the soil may deform, but it will return to its original shape once the load is removed. This behavior is typical of granular soils like sands and gravels. O. Plastic deformation. In some cases, the soil may undergo permanent deformation when subjected to a load. This is more common in cohesive soils like clays, which can undergo plastic flow. 2. Shear strength and failure. The shear strength of soil refers to its ability to resist sliding or shearing under applied forces. This property depends on the soil's composition, structure, and moisture content. When soil is subjected to shear stresses that exceed its shear strength, failure occurs, which may lead to slope instability, foundation settlement, or other geotechnical problems. 3. Consolidation and settlement. Soils, particularly clays, may experience significant settlement over time under the influence of static loads. This is due to consolidation, a time-dependent process in which water is squeezed out of the soil's pore spaces, leading to a reduction in volume and settlement. Granular soils tend to experience less consolidation. 4. Permeability and fluid flow. The permeability of soil determines how easily water or other fluids can flow through it. Soils with high permeability, like sands and gravels, allow rapid drainage and are often used in drainage systems. Cohesive soils, like clays, have low permeability, which can lead to water retention and increased potential for swelling or shrinkage. 2.1.5 The role of soil composition and structure in geotechnical design. The composition and structure of soil significantly influence the design of geotechnical structures. For example, granular soils, sand and gravel, are often chosen for foundations due to their high bearing capacity and low compressibility, whereas cohesive soils, clays, may require ground improvement techniques to mitigate settlement. Soil compaction, drainage, and the risk of liquefaction must all be considered when designing foundations and other earthworks. In conclusion, understanding soil structure and composition is fundamental to geotechnical engineering. By examining the various components of soil and how they interact, engineers can better predict soil behavior under different conditions, thereby ensuring the stability and safety of geotechnical structures. This knowledge provides the foundation for advanced design techniques and methodologies in modern geotechnical practice. Chapter 2: Soil Mechanics Revisited. 2.2 Classification of Soils. Soil classification is a fundamental aspect of geotechnical engineering, as it provides critical insights into the properties and behavior of soils. Proper classification helps engineers assess soil performance, design foundations, and determine appropriate construction techniques. In this section, we explore the primary systems used for soil classification, focusing on their relevance to engineering applications. 2.2.1 Importance of soil classification. Soil classification serves multiple purposes in geotechnical engineering. Understanding soil behavior. Classifying soils allows engineers to predict their behavior under different conditions such as loading, compaction, and drainage. Guiding design decisions. The classification helps determine suitable foundation types, construction methods, and whether additional soil improvement techniques, e.g., compaction or stabilization, are needed. Ensuring site safety. Proper classification aids in assessing potential issues such as settlement, soil liquefaction, or slope stability failures. Selecting appropriate testing. The classification system guides engineers in selecting the appropriate tests for determining soil strength, permeability, and compressibility. 2.2.2 Soil classification systems. Several systems are used worldwide to classify soils. The two most widely used systems in geotechnical engineering are the Unified Soil Classification System, USCS, and the ASHTO Soil Classification System. Both systems classify soil based on particle size, distribution, plasticity, and other properties. 2.2.2.1 Unified Soil Classification System USCS. The USCS is one of the most common classification systems, particularly for engineering purposes. It divides soils into two major groups: coarse-grained soils and fine-grained soils, based on the percentage of particles larger than 0.075 millimeters, the number 200 sieve. Coarse-grained soils, more than 50% particles retained on the number 200 sieve. Gravel, G soil with particles larger than 4.75 millimeters. Well-graded gravel, GW gravel with a good distribution of particle sizes. Poorly graded gravel, GP gravel lacking sufficient variation in particle sizes. Gravel sand mixtures, GM a mixture of gravel and sand, with gravel being the dominant component. Sand, S soil with particles ranging from 0.075 millimeters to 4.75 millimeters. Well-graded sand, SW a sand with a variety of particle sizes. Poorly graded sand, SP sand lacking sufficient variation in particle sizes. Silta sand, SM sand with a significant amount of silt content. Clayey sand, SC sand with a significant amount of clay content. Fine-grained soils, more than 50% particles passing through the number 200 sieve. O clay, sees soil with particles smaller than 0.002 millimeters. Clays exhibit high plasticity and cohesion. Low plasticity clay, Cl clay with low plasticity. High plasticity clay, Ch clay with high plasticity, often more susceptible to shrinkage and swelling. O silt, M soil with particles ranging from 0.002 millimeters to 0.075 millimeters. Silts exhibit less plasticity than clays but are cohesive. Low plasticity silt, Ml silt with low plasticity. High plasticity silt, Mh silt with high plasticity. In addition, the USCS system uses a two-letter classification code to indicate soil type, such as GW, well-graded gravel, or CL, low plasticity clay, with two X's that provide further details about the soil's characteristics. 2.2.2.2 ASHTO Soil Classification System. The ASHTO system is commonly used in the United States for road and highway construction. It classifies soils based on their suitability for use in pavement subgrades and embankments. Soils are categorized into groups A1 to A7 based on particle size, distribution, and plasticity. The classification is determined using the following criteria. Group A1, soils that are highly granular and have excellent drainage. Characteristics. These soils typically consist of clean sands and gravels with a low plasticity content. OA1A, gravelly soils with low fines content. OA1B, sandy soils with a low fines content. Group A2, soils with moderate to high amounts of fines but still suitable for use as subgrade materials. These soils often include mixtures of gravel and sand with limited silt or clay content. OA2-4, sands with gravel or gravelly sands. OA2-6, clayey sands. Group A3, siltous soils with a greater proportion of silt and clay than in Group A2, but still suitable for use in road construction, though with less desirable engineering properties. OA3, fine silts or siltous sands. Group A4 to A7, these soils consist of silts and clays with high plasticity and are not ideal for subgrade material because of their high compressibility and low drainage capabilities. OA4, silt with low plasticity. OA5, siltous soils with higher plasticity. OA6, clays with moderate plasticity. OA7, clays with high plasticity, which are most susceptible to shrinking and swelling. The ASHTO system uses a combination of grain size distribution and Atterberg limits plasticity index to classify soil into these groups. Soils in groups A1 and A2 are generally preferred for road construction due to their better compaction and drainage properties. 2.2.2.3 Atterberg limits. Atterberg limits are used to classify fine-grained soils, silts, and clays based on their plasticity characteristics. The primary Atterberg limits include liquid limit, LL, the moisture content at which soil changes from a plastic state to a liquid state. It reflects the soil's water retention capacity and plasticity. Plastic limit, PL, the moisture content at which soil begins to exhibit plastic behavior, i.e., it can be rolled into a thread. Plasticity index, PI, the difference between the liquid limit and plastic limit, PI equals LL. PO. The plasticity index indicates the soil's potential for deformation and swelling. Soils with high plasticity indices, PI greater than 15, are more likely to exhibit significant volume change, shrinkage, and swelling when wet or dry. These soils are typically classified as high plasticity clays, CH, in the USCS or A7 in the ASHTO system. 2.2.3 Particle size distribution and its role in classification. Particle size distribution, gradation, plays a critical role in the classification of soil. A soil's gradation affects its strength, compaction, and permeability. Soil can be classified as well-graded, contains a range of particle sizes, resulting in a dense, stable structure with fewer voids. Poorly graded, lacks a variety of particle sizes and may have excessive voids, leading to poor stability and low shear strength. Gradation is typically determined using sieve analysis, which involves passing a sample of soil through a series of sieves with different mesh sizes. The results are used to create a particle size distribution curve that helps engineers classify the soil and predict its behavior. 2.2.4 Other soil classification methods. In addition to the USCS and ASHTO systems, there are other specialized classification methods used for specific purposes. ISO classification system, used in some international standards to classify soils based on their properties. British Standard Classification, BS 1377, a classification system used in the UK for soil testing, which incorporates tests for both coarse-grained and fine-grained soils. 2.2.5 Summary of soil classification. Soil classification is a powerful tool for understanding soil behavior and guiding geotechnical design. The two primary classification systems, USCS and ASHTO, serve different purposes, with USCS being focused on engineering properties and ASHTO mainly used for road and highway design. The classification of soils is influenced by factors such as particle size distribution, plasticity, and soil composition, with classifications providing important insights into soil strength, compressibility, drainage, and other key characteristics. By understanding the classification systems and the properties they reflect, engineers can make more informed decisions regarding site preparation, foundation design, and soil improvement, ensuring safe and efficient construction practices. Chapter 2: Soil Mechanics Revisited. 2.3 Index Properties of Soils. Index properties are essential characteristics of soil that help engineers classify and predict the behavior of soils under various conditions. These properties do not directly describe soil strength, compressibility, or permeability, but provide useful insights into soil's overall behavior, which is critical for design purposes. In geotechnical engineering, index properties are primarily used to classify soils, understand their physical and mechanical characteristics, and predict how they will respond to loading, moisture variations, and other environmental conditions. 2.3.1 Overview of Index Properties. Index properties are fundamental parameters that can be easily measured and used to assess soil characteristics. The key index properties of soil include grain size distribution or particle size distribution, Atterberg limits, liquid limit, plastic limit, plasticity index, specific gravity, density, bulk density and dry density, moisture content. These properties help in classifying soils and assessing their suitability for construction projects. The following sections provide detailed descriptions of each index property. 2.3.2 Grain size distribution, particle size distribution. Grain size distribution is a measure of the relative proportions of different-sized particles in a soil sample. This property helps to classify the soil as either coarse-grained, sand or gravel, or fine-grained, silt or clay, and it is crucial for determining soil behavior such as permeability and compaction characteristics. Sieve analysis, a common method used to determine the grain size distribution of coarse-grained soils, gravel and sand. Soil is passed through a series of sieves with different mesh sizes, and the amount of soil retained on each sieve is weighed. Hydrometer analysis, used for fine-grained soils, clay and silt. This test measures the rate at which particles settle in water. It helps determine the percentage of particles that are finer than 0.075 millimeters, the number 200 sieve size. The grain size distribution is typically presented as a particle size distribution curve. This curve plots the cumulative percentage of soil passing through the sieves against the sieve size. The shape of the curve helps engineers assess the soil's gradation. Well-graded soils have a broad range of particle sizes and typically provide better compaction and stability. Poorly graded soils are dominated by a few particle sizes and may have excessive voids, leading to reduced stability and increased settlement. 2.3.3 Atterberg limits. Atterberg limits are used to assess the plasticity and behavior of fine-grained soils. specifically clays and silts. These limits help in understanding the soil's ability to undergo deformation without cracking or crumbling. The three primary Atterberg limits are: 1. Liquid limit, LL, the moisture content at which the soil changes from a plastic state to a liquid state. In this state, the soil flows like a liquid. The liquid limit is determined by the Casagrande cup method, where a soil sample is placed in a cup and a groove is made along the soil surface. The cup is then dropped, and the liquid limit is defined as the moisture content at which the groove closes after 25 drops. 2. Plastic limit, PL, the moisture content at which the soil changes from a semi-solid to a plastic state. At this point, the soil can be rolled into threads without crumbling. The plastic limit is determined by rolling a small amount of soil between the fingers until it forms a thread of 3 millimeters in diameter. The moisture content at which this occurs is the plastic limit. 3. Plasticity index, PI, the difference between the liquid limit and the plastic limit, PI, equals LLPL. The plasticity index indicates the soil's potential for deformation and its tendency to undergo swelling or shrinkage. Soils with a high PI, such as clays, tend to exhibit more shrinkage and swelling compared to soils with a low PI, such as silts. The Atterberg limits provide an indication of the soil's plasticity and workability, with higher plasticity soils being more difficult to compact and requiring special treatment in foundation design. 2.3.4 Specific gravity. Specific gravity, G, of soil is the ratio of the density of soil particles to the density of water. It is an important parameter in geotechnical calculations because it allows engineers to calculate other properties of the soil, such as void ratio and degree of saturation. Standard specific gravity, the typical value for specific gravity for most soil particles is around 2.65, but it can vary depending on the mineral composition of the soil, e.g., clay, sand, or gravel. Fine-grained soils, clays, and silts typically have a higher specific gravity compared to coarse-grained soils. Specific gravity is typically measured using a pycnometer or density bottle, where a known volume of soil is weighed and compared to the mass of an equal volume of water. 2.3.5 Density, bulk density, and dry density. Density refers to the mass per unit volume of a soil sample and is crucial for understanding soil compaction and stability. 1. Bulk density, ρ_b, the mass of soil per unit volume, including both solids and voids. It is calculated as bulk density equals mass of soil volume of soil \text. Bulk density equals \frac \text mass of soil \text volume of soil. Bulk density provides information on how compact the soil is and is related to its permeability, and strength. 2. Dry density, ρ_d, the mass of soil per unit volume of solid particles. It is calculated as dry density equals mass of dry soil volume of soil / text. Dry density equals /frac / text mass of dry soil / text volume of soil. Dry density is important for determining the soil's compaction and helps in calculating other properties like void ratio and degree of saturation. Both bulk and dry densities are used to assess soil compaction, which is essential for ensuring proper support in foundation design and earthworks. 2.3.6 Moisture content. Moisture content is the ratio of the weight of water present in the soil to the weight of dry soil. It is a key property that influences the soil's strength, compressibility, and plasticity. The moisture content is calculated as moisture content equals weight of water weight of dry soil times 100 / text. Moisture content equals /frac / text weight of water / text weight of dry soil / times 100. Moisture content is measured by drying a soil sample in an oven at a temperature of 105 degrees Celsius to 110 degrees Celsius until the sample reaches a constant weight. Moisture content plays a crucial role in soil classification, especially for fine-grained soils, and is used to determine the soil's compaction, shrinkage, and swelling potential. 2.3.7 Summary of Index Properties. The index properties of soils: grain size distribution, Atterberg limits, specific gravity, density, and moisture content are vital tools for understanding soil behavior and classifying it for engineering purposes. These properties help engineers classify soils into coarse-grained or fine-grained categories, which in turn influences the design of foundations and other geotechnical structures. Predict soil behavior, such as its compaction, permeability, and swelling potential. Determine suitable construction techniques by identifying whether soil improvement methods, like compaction or stabilization, are necessary. By measuring and analyzing these index properties, geotechnical engineers can make informed decisions regarding the suitability of soil for various applications, ensuring the safety and stability of the built environment. Chapter 2: Soil Mechanics Revisited. 2.4 Soil Behavior and Constitutive Models. Soil behavior is complex and varies under different loading and environmental conditions. The way soils respond to mechanical stresses, whether they deform elastically, plastically, or show significant volume changes, depends on their composition, structure, and the nature of the applied load. Understanding soil behavior is crucial for geotechnical engineers to design foundations, slopes, embankments, and other structures. Constitutive models play a central role in characterizing and predicting the stress-strain behavior of soils under various conditions. 2.4.1 Overview of soil behavior. Soils exhibit nonlinear, time-dependent behavior, and their response to loading can be categorized into several distinct phases. 1. Elastic behavior. In the elastic phase, soil deforms proportionally to the applied stress and returns to its original shape once the stress is removed. This behavior is typical at low stress levels or in short-term loading situations. 2. Plastic behavior. At higher stress levels, soils may undergo irreversible deformations even after the applied stress is removed. This is known as plastic deformation. Plastic behavior is prominent in clays and other fine-grained soils that experience significant plasticity. 3. Creep and time-dependent deformation. Soils may exhibit slow, continuous deformation over time under constant load. This phenomenon, known as creep, is particularly noticeable in clays and other cohesive soils, which have high compressibility and low permeability. 4. Stress-dependent behavior. Soil behavior is also stress-dependent, meaning that the response to loading changes with the magnitude and direction of the applied stress. For example, soil may behave de-errantly under compressive versus shear stresses. 5. Volume change. Soils may undergo changes in volume due to loading, moisture content variations, or other external factors. Compaction results in a decrease in volume, while swelling can cause an increase in volume. This behavior is particularly significant in expansive clays and silts. 6. Hysteresis. Soils often exhibit hysteresis, which refers to the de-errance in the loading and unloading paths. This is typically observed in soils subjected to cyclic loading, such as in foundation systems subjected to TRA-IC or seismic loading. 2.4.2 Factors influencing soil behavior. Several factors influence soil behavior, including soil type. The composition and gradation of soil particles significantly affect its behavior. Coarse-grained soils, such as sands and gravels, generally exhibit less volume change under loading compared to fine-grained soils, such as clays and silts, which can experience significant expansion or shrinkage due to changes in moisture content. Consolidation. Fine-grained soils such as clays often undergo consolidation, a time-dependent process in which pore water is expelled under sustained load, leading to a decrease in volume. Consolidation can take days, months, or even years, depending on the soil's permeability and the magnitude of the applied load. Shear strength. Soil's ability to resist shearing forces determines its stability under loading conditions. The shear strength of soil is influenced by factors such as moisture content, soil type, and the presence of cohesive forces in clays or friction in granular soils. Permeability. The rate at which water flows through soil is crucial in determining how a soil will behave under loading conditions. High permeability soils such as sands and gravels drain quickly, while low permeability soils such as clays retain water and experience changes in pore pressure during loading. 2.4.3 Constitutive models for soil behavior. Constitutive models describe the relationship between stress and strain in materials. In the context of soils, these models are essential for predicting soil response to various loading conditions, including compressive, shear, and cyclic loads. Soil constitutive models range from simple linear elastic models to more complex nonlinear and time-dependent models. 2.4.3.1 Elastic models. In an elastic model, soil is assumed to behave in a linear manner, meaning that the stress is directly proportional to strain. Elastic models are generally used for small strains and short-term loading conditions, where the soil does not undergo permanent deformation. The simplest elastic model is described by Hooke's law, which relates the stress and strain through the Young's modulus, E, for normal stresses, and the shear modulus, G, for shear stresses. Young's modulus, E, a measure of soil steadiness in response to compressive stresses. It is a constant for a given material and is related to the strain produced by a given stress. Shear modulus, G, a measure of soil steadiness in response to shear stresses. While elastic models are useful for small strain analysis, they fail to capture the nonlinear and time-dependent behavior of most soils under larger strains. 2.4.3.2 Mohr-Coulomb model. The Mohr-Coulomb model is widely used in geotechnical engineering to describe the shear strength of soils. It expresses the shear strength, tau/tau, as a function of the normal stress, sigma/sigma, and the cohesion, Cc, and internal friction angle, phi/phi, of the soil. The equation is given by tau equals C plus tan phi /tau equals C plus /sigma /tan /phi, where tau/tau is the shear strength. Cc is the cohesion, which is the internal bonding of soil particles, more significant in clays. Phi/phi is the angle of internal friction, which measures the soil's resistance to sliding, more significant in granular soils. Sigma/sigma is the normal stress. The Mohr-Coulomb model is simple and effective for estimating the shear strength of soils under steady-state conditions, such as in slope stability analyses or bearing capacity calculations. However, it does not fully account for the nonlinear, time-dependent, and volume change behavior of soils. 2.4.3.3 Kamklay model. The Kamklay model is a more advanced constitutive model that is often used for clays and other fine-grained soils. This model accounts for both plastic and elastic behavior, incorporating the effects of consolidation and volume changes. The CAMCLA model is based on the concept of yield surfaces and plastic flow, describing how soils behave during both loading and unloading cycles. The key features of the CAMCLA model include elastic loading. When the stress is below the yield surface, the soil behaves elastically. Plastic flow. When the stress exceeds the yield surface, the soil undergoes plastic deformation, leading to permanent changes in the soil structure. Pre-consolidation pressure. The model considers the history of loading, with soils experiencing less deformation when the applied stress is lower than the maximum. Past stress, pre-consolidation. The CAMCLA model is widely used for modeling the behavior of clays under both monotonic and cyclic loading conditions. 2.4.3.4 Hardening/softening models. Soils, particularly those subjected to large strains, may exhibit hardening, increased steamness, or softening, decreased steamness behavior as a result of internal changes in the soil structure. Hardening models, such as the Drucker-Prager model or the Bookman model, capture the soil's response as the material strengthens or weakens under loading. These models are used to describe complex soil behaviors, including post-peak softening in stress-strain curves or strain hardening due to soil compaction. 2.4.3.5 Hypoplastic models. Hypoplastic models are used for describing the behavior of granular materials and highly nonlinear soils. Unlike classical plasticity models, hypoplastic models do not rely on the concept of yield surfaces. They instead describe the behavior of soils using a set of empirical rules that depend on stress and strain, capturing the influence of strain rate, density, and other factors. Hypoplastic models are particularly useful for modeling sand and gravel, which exhibit complex behavior under both loading and unloading conditions. 2.4.4 Applications of constitutive models. Constitutive models are used in a variety of engineering applications to predict soil behavior and inform design decisions. Some key applications include foundation design. Constitutive models help engineers determine the appropriate design parameters for foundations, considering factors like soil steamness, shear strength, and consolidation. Slope stability analysis. Models help predict the stability of slopes by simulating the response of soils to different loading conditions, including changes in pore water pressure. Earthquake engineering. During seismic events, soils can experience significant dynamic loading. Constitutive models, particularly those that account for cyclic behavior and hysteresis, are crucial in evaluating the performance of foundations and embankments during earthquakes. Settlement predictions. Constitutive models help in predicting the settlement of foundations, embankments, or other structures subjected to long-term loading. 2.4.5 Summary of Soil Behavior and Constitutive Models. Soil behavior is complex and nonlinear, influenced by factors such as soil type, loading, conditions, and environmental influences. Constitutive models are essential tools in understanding and predicting soil response to stress and strain, enabling engineers to design safe and efficient structures. From simple elastic models to more sophisticated models like Morcoulomb, Cam Clay, and hypoplastic models, these tools provide valuable insights into the mechanical properties and long-term behavior of soils. Chapter 2: Soil Mechanics Revisited. 2.5 Soil Stress-Strain Behavior. Soil stress-strain behavior is a fundamental concept in geotechnical engineering that describes how soils deform under different types of loading. Understanding this behavior is critical for the design of foundations, embankments, slopes, and other civil engineering structures. Soil, unlike other materials such as metals or concrete, exhibits a highly nonlinear, complex, and often time-dependent response to stress. The stress-strain curve for soil can vary depending on factors such as soil type, loading rate, and environmental conditions. This section will explore the key aspects of soil stress-strain behavior, including the general principles, types of stress-strain responses, and the factors that influence this behavior. 2.5.1 Basic Concept of Stress and Strain in Soils. Stress. Sigma stress is the force per unit area applied to the soil. It can be classified into normal stress, acting perpendicular to a surface, and shear stress, acting parallel to a surface. In soil mechanics, stress is often described in terms of vertical and horizontal components, particularly for undrained or drained loading conditions. Strain. Epsilon strain is the deformation or change in shape of the soil in response to applied stress. It is typically expressed as the ratio of the change in length to the original length, or the change in volume to the original volume. Soil stress-strain behavior is often depicted graphically, where stress is plotted on the y-axis and strain on the x-axis. This curve can reveal important information about soil steadiness, strength, and its response to different types of loading. 2.5.2 Types of soil stress-strain responses. Soils exhibit various types of stress-strain responses depending on their composition, structure, and loading conditions. These responses can generally be classified into three main categories. 1. Elastic behavior. In the elastic region, the stress is directly proportional to the strain, and the soil returns to its original state when the load is removed. This is similar to the behavior of other materials such as metals, though the elastic region of soils is typically smaller in terms of strain. Young's modulus E, is used to quantify the soil steepness in this region. In soils, this modulus is not constant and typically decreases as the soil undergoes more deformation. O elastic modulus, E, and shear modulus, G. These are parameters used to describe the soil's ability to resist deformation in response to applied stress. 2. Plastic behavior. When the applied stress exceeds the elastic limit, the soil enters the plastic region. In this region, deformation becomes permanent and the soil does not return to its original state when the stress is removed. Yield point. The point at which soil transitions from elastic to plastic behavior is called the yield point. This is typically observed in soils such as clays that undergo significant plastic deformations. Plastic deformation. Fine-grained soils, clays and silts exhibit considerable plastic deformation under stress, meaning that they can undergo large amounts of strain without failure or rupture. 3. Cyclic and time-dependent behavior. Soils exhibit cyclic behavior when subjected to repeated loading and unloading, such as in foundations under TRA-IC or in earthquake loading conditions. Hysteresis. This is the phenomenon where the soil follows adherent paths during loading and unloading. The soil may not fully recover its previous state after unloading, leading to energy dissipation. Creep. Over time, soils may continue to deform slowly under constant load, even after the initial elastic and plastic deformations have occurred. This time-dependent deformation is especially significant in cohesive soils like clays. 2.5.3 Stress-strain curve of soils. The stress-strain curve for soils varies depending on the soil type and the loading conditions. However, most stress-strain curves for soils exhibit certain common characteristics. 1. Initial linear region, elastic region. At small strains, the soil exhibits linear elastic behavior and the stress is proportional to the strain. This region is characterized by a constant slope, representing the soil's modulus of elasticity, E. 2. Nonlinear plastic region. Beyond the elastic limit, the stress-strain curve becomes nonlinear, and the soil begins to exhibit permanent plastic deformation. The curve flattens as the soil experiences yielding and hardening. 3. Failure or ultimate stress. In some soils, particularly under compressive loading, the curve will eventually reach a point of failure. This corresponds to the maximum stress the soil can withstand before rupture or collapse. Beyond this point, the soil may experience a drastic decrease in stress with increased strain, softening, or it may fail through shear rupture. The general shape of the stress-strain curve for typical soils can be seen as follows. For granular soils, e.g., Sand and gravel, these materials exhibit a steep initial rise in the stress-strain curve, followed by a gradual leveling. Granular soils typically do not undergo significant plastic deformation, but may exhibit dilatancy, where the soil volume increases during shear deformation. For cohesive soils, e.g., clays often show more pronounced plastic deformation. The stress-strain curve for clays tends to have a more curved, gradual rise in the elastic region, followed by a yield point where plastic deformation becomes significant. 2.5.4 Factors affecting soil stress-strain behavior. Several factors influence the stress-strain behavior of soils. 1. Soil type and gradation. Coarse-grained soils, sands, and gravels. These soils exhibit relatively high steepness and are less prone to significant plastic deformation. Their stress-strain behavior is more elastic and less affected by factors such as moisture content. Fine-grained soils, clays, and silts. These soils have lower steepness and more significant plastic behavior, especially at higher moisture contents. They also exhibit time-dependent behaviors such as consolidation and creep. 2. Soil density and compaction. The density of soil, which is influenced by compaction, has a direct impact on its stress-strain behavior. Higher compaction typically leads to steer soil with a higher modulus of elasticity and reduced deformation under load. 3. Moisture content. For cohesive soils, moisture content plays a significant role in determining the soil's plasticity and strength. Soils with higher moisture content exhibit reduced steepness and increased plasticity, leading to more substantial deformations under load. 4. Stress history. Soils that have been subjected to previous loading, such as in previously consolidated soils, will behave differently compared to soils that have not been stressed before. The pre-consolidation pressure, or yield stress, significantly affects the current behavior of the soil. 5. Loading conditions. The rate of loading and the type of load, static or dynamic, can significantly affect soil behavior. For example, clays subjected to rapid loading, e.g., during an earthquake, may exhibit reduced strength due to the inability of pore water to dissipate quickly, leading to excess pore pressure buildup and reduced effective stress. 6. Consolidation and volume change. The consolidation behavior of soils, especially in fine-grained materials like clays, is an important consideration in stress-strain analysis. Soils undergo volume change during consolidation, which affects their steepness and strength during loading. 2.5.5 Models for stress-strain behavior of soils. Several models are used to simulate the stress-strain behavior of soils in geotechnical engineering. 1. Elastic models. These models are useful for small deformations and are represented by the linear relationship between stress and strain, Hooke's law. They are commonly used in situations where the soil is expected to return to its original state once the load is removed. 2. Plasticity models. These models, such as the Moore-Coulomb and Camp-Clay models, account for the irreversible deformations of soils. They are particularly useful in modeling the behavior of soils under large deformations, such as in slope, stability, or foundation design. 3. Viscoelastic and creep models for time-dependent behavior, such as in soils subjected to sustained loads, e.g., embankments or foundations. Viscoelastic models and creep models are used to simulate the delayed response of soils to applied stresses. 4. Hypoplastic models. These models describe the behavior of granular soils without relying on yield surfaces. They are particularly useful for modeling granular materials under complex loading conditions. 2.5.6 Summary of soil stress-strain behavior. Soil stress-strain behavior is fundamental to understanding the deformation characteristics of soils under loading conditions. This behavior can vary significantly depending on soil type, loading conditions, and environmental factors. The stress-strain curve reveals valuable information about soil steepness, plasticity, and failure mechanisms, and is critical for designing safe and effective geotechnical structures. Constitutive models, such as elastic, plastic, and time-dependent models, are used to simulate soil behavior, allowing engineers to make informed decisions in foundation design, slope stability analysis, and other geotechnical applications. Chapter 2: Soil Mechanics Revisited. 2.6 Advanced Soil Testing Methods. Soil testing is an essential part of geotechnical engineering that helps in understanding the properties and behavior of soils under various conditions. Advanced soil testing methods provide more accurate, detailed, and reliable data that are critical for designing safe and efficient structures, such as foundations, embankments, and slopes. These advanced testing techniques are especially valuable in complex soil conditions, such as those found in deep foundations, unsaturated soils, or under cyclic loading conditions. This section explores some of the most important advanced soil testing methods used to assess soil properties, including both laboratory and in situ testing techniques. 2.6.1 Laboratory Testing Methods. Laboratory tests are designed to simulate the behavior of soil under controlled conditions and allow for accurate measurements of soil properties. These tests typically involve extracting soil samples from the field and testing them in the lab under various loading and environmental conditions. 2.6.1.1 Triaxial Compression Test. Purpose: The triaxial test is one of the most widely used laboratory tests to determine the shear strength and stress-strain behavior of soils. It simulates the conditions of soils in the field subjected to multiaxial stresses. Method: a cylindrical soil specimen is placed in a chamber where confining pressure is applied in all directions, and axial stress is applied along the length of the specimen. The test can be conducted under diuretic drainage conditions, undrained or drained, and loading rates, constant or variable. Applications: the triaxial test is crucial for determining the cohesion and friction angle of soils, as well as the stress-strain behavior under various loading conditions. 2.6.1.2 Direct Shear Test. Purpose: the direct shear test is used to measure the shear strength of soils by applying a normal force and gradually increasing the shear force until the specimen fails. Method: a soil sample is placed in a shear box, and the applied normal stress is gradually increased. The soil is then sheared along a horizontal plane, and the shear strength is measured. Applications: it is widely used for determining the shear strength parameters of granular soils, particularly for foundation design and slope stability analysis. However, the test may be less accurate for cohesive soils, as the failure plane is fixed and may not represent the actual failure surface in these soils. 2.6.1.3 Consolidation Test, Pedometer Test. Purpose: the consolidation test is used to determine the compressibility of fine-grained soils, particularly clays, under a constant load and to estimate the settlement of foundations over time. Method: a soil sample is placed in a cylindrical pedometer apparatus. The specimen is subjected to incremental loads, and the change in height, or settlement, is measured. This test can provide data on coefficient of consolidation, compressibility, and pre-consolidation pressure. Applications: the consolidation test is essential for predicting settlement in saturated soils, especially in the design of embankments and shallow foundations. 2.6.1.4 Unconsolidated Undrained UU Test. Purpose: this test is used for measuring the shear strength of cohesive soils such as clays under undrained conditions, which simulates situations where there is insufficient time for pore water to dissipate. Method: the specimen is subjected to an axial load without allowing drainage, and the resulting shear strength is measured. This test is typically used for short-term loading conditions such as in foundations subjected to rapid load application. Applications: it is particularly useful for evaluating the strength of clays under rapid loading, such as during seismic events or sudden load applications. 2.6.1.5 Soil Permeability Test. Purpose: the permeability test is used to measure the rate at which water can flow through soil. This property is critical in understanding groundwater movement, soil consolidation, and drainage systems. Method: there are different types of permeability tests, including the constant head test for granular soils and the falling head test for fine-grained soils. These tests involve measuring the amount of water passing through a soil sample over time under controlled conditions. Applications: permeability tests are critical in determining the effectiveness of drainage systems, the risk of soil erosion, and in predicting settlement rates in fine-grained soils. 2.6.1.6 Stress Path Test. Purpose: the stress path test is used to analyze the soil behavior under varying stress conditions and to understand how the soil responds to different loading sequences. Method: the test involves applying a series of incremental loading steps that simulate real-life loading conditions and observing the change in stress and strain along a given stress path. Applications: this test is essential for evaluating the stability of soils under non-constant loading conditions, such as during earthquake loading, cyclic loading, or fluctuating pressures. 2.6.2 In situ testing methods. In situ testing methods are used to measure soil properties directly at the site of construction. These methods are generally faster and provide a more realistic representation of soil behavior because they are conducted under actual field conditions. 2.6.2.1 Standard Penetration Test (SPT). Purpose: the Standard Penetration Test (SPT) is one of the most common in situ tests for measuring soil resistance and estimating soil properties. Method: a split-barrel sampler is driven into the soil using a standard hammer, and the number of blows required to drive the sampler a certain distance is recorded as the N value. This value can be used to estimate soil consistency, density, and strength. Applications: the SPT is used extensively for evaluating the relative density of granular soils, the strength of cohesive soils, and for preliminary site characterization in foundation design. 2.6.2.2 Cone Penetration Test (CPT). Purpose: the Cone Penetration Test (CPT) provides continuous measurements of soil resistance as a cone is pushed into the ground. Method: a cone-shaped penetrometer is pushed into the soil at a constant rate, and resistance is measured continuously during penetration. The cone resistance QC and skin friction are recorded, providing detailed information about soil strength and stratigraphy. Applications: the CPT is used to measure soil stratigraphy, estimate soil strength parameters, and assess the bearing capacity of the soil for foundation design. It is often used in soft or medium-C soils where other methods might be less effective. 2.6.2.3 Vein Shear Test. Purpose: The vane shear test is used to measure the undrained shear strength of cohesive soils, particularly clays. Method: a four-bladed vane is inserted into the soil and rotated, and the torque required to cause failure is recorded. The resulting value is used to determine the undrained shear strength of the soil. Applications: the vane shear test is used to assess the strength of soft clays in situ, and is often employed in deep foundation design, slope stability analysis, and the evaluation of soil improvement techniques. 2.6.2.4 Pressure meter test. Purpose: the pressure meter test is used to assess the soil's stress-strain behavior and determine the deformability of the soil in situ. Method: a cylindrical probe is inserted into a borehole and pressure is applied to expand the probe. The changes in pressure and volume are recorded to determine the soil's response to expansion. Applications: this test is particularly useful for assessing the deformability and shear modulus of soils, as well as for evaluating the behavior of granular soils and deep foundations. 2.6.2.5 Geophysical testing, seismic refraction and resistivity tests. Purpose: geophysical tests are used to obtain information about subsurface soil properties such as density, compressive wave velocity, and shear wave velocity. Method: seismic refraction tests involve measuring the time it takes for seismic waves to travel through the soil, which can be used to estimate soil stiffness. And stratigraphy: electrical resistivity tests measure the soil's resistance to an electric current, which provides insight into the soil's moisture content and composition. Applications: geophysical tests are used for large-scale site investigations, particularly when invasive methods are impractical. They provide useful data for assessing the subsurface structure, soil stratigraphy, and seismic site characterization. 2.6.3 Summary of advanced soil testing methods. Advanced soil testing methods provide essential data for understanding the behavior of soils under direct conditions. Laboratory tests such as the triaxial compression test, consolidation test, and shear tests provide valuable insights into the strength, compressibility, and deformation characteristics of soils. In situ testing methods such as the cone penetration test, vane shear test, and pressure meter test allow for direct measurement of soil properties under field conditions, making them invaluable tools for site characterization and foundation design. Together, these advanced testing techniques play a crucial role in ensuring the safety and effectiveness of geotechnical engineering projects. Chapter 3: Site Characterization and Investigation. 3.1 Geotechnical Site Investigation Methods. Geotechnical site investigations are crucial in gathering essential information about the soil and rock properties of a site before any construction begins. Proper site Characterization ensures the design of safe and effective structures by understanding them. Soil's behavior, load-bearing capacity, settlement potential, and overall stability under direct conditions. A well-conducted investigation helps identify potential risks, such as subsidence, liquefaction, or slope failure, and allows engineers to plan and design appropriate mitigation measures. This section outlines the main geotechnical site investigation methods, which include both field and laboratory testing techniques used to assess subsurface conditions. 3.1.1 Preliminary Site Survey and Desk Study. Before conducting any in-field testing, a preliminary site survey and desk study are carried out. This initial phase helps in understanding the regional geology, hydrology, and historical land use, which can provide useful insights into possible subsurface conditions. A desk study typically involves reviewing historical maps, previous construction, land use, and past soil issues, topographic and geological maps, to identify potential hazards, such as fault lines, groundwater table, or floodplains. Previous investigations, reviewing prior geotechnical reports or studies from surrounding sites. This background research helps identify areas of concern and guides the design of the site. Specific investigation. 3.1.2 Field Investigation Methods. Field investigations are performed to obtain direct data from the site. These methods include drilling, sampling, and in situ tests that provide more accurate, site-specific information on soil and rock properties. Some of the most commonly used field investigation techniques include 3.1.2.1 Borehole drilling and sampling. Purpose: boreholes are drilled to obtain soil and rock samples at various depths to determine the stratigraphy, soil composition, and groundwater conditions. Method: a rotary or percussion drilling rig is used to create a borehole. Soil samples are collected at different depths, often using split-barrel samplers or undisturbed core samplers for cohesive soils. Applications: boreholes provide valuable information about the soil profile, depth of bedrock, and groundwater table. The samples collected can be used for laboratory testing to measure properties such as shear strength, compaction, and permeability. 3.1.2.2 Standard Penetration Test (SPT). Purpose: the SPT is a widely used in situ testing method to assess the relative density and shear strength of soils, particularly granular soils like sands and gravels. Method: a split-barrel sampler is driven into the soil using a hammer, and the number of blows required to advance the sampler a specified distance, typically 300 millimeters, is recorded. This N value provides an indication of soil steepness and strength. Applications: the SPT is often used in shallow foundation design and site characterization for understanding soil stratigraphy, relative compaction, and liquefaction potential in earthquake-prone areas. 3.1.2.3 Cone Penetration Test (CPT). Purpose: the CPT provides continuous measurement of soil resistance and is a highly effective method for evaluating soil strength and stratigraphy. Method: a cone penetrometer with an attached pore pressure sensor is pushed into the ground at a constant rate. The cone resistance, QC, frictional resistance, FS, and pore pressure are continuously measured as the probe advances. Applications: the CPT is used to assess soil type, bearing capacity, and liquefaction potential. It is particularly useful in soft soils or areas with a shallow groundwater table, where traditional drilling methods may be less effective. 3.1.2.4 Vein Shear Test. Purpose: this test measures the undrained shear strength of cohesive soils, particularly clays, in the field. Method: a four-bladed vein is inserted into the soil, and the torque required to shear the soil is measured. The undrained shear strength is then calculated from the measured torque. Applications: the vein shear test is especially useful for soft clays, peat, and other fine-grained soils. It is often used for slope stability analysis and deep foundation design in clays. 3.1.2.5 Pressure Meter Test. Purpose: the pressure meter test is used to measure the deformability and shear modulus of soils in situ, particularly granular materials. Method: a cylindrical probe is inserted into a borehole and pressure is applied to expand the probe. The pressure and volume changes are recorded to determine the soil's response to deformation. Applications: the pressure meter test is used to assess foundation bearing capacity, soil steepness, and deformation characteristics in granular soils or deep foundation applications. 3.1.2.6 Geophysical Methods: seismic refraction, resistivity, and ground penetrating radar. Purpose: geophysical methods are used to obtain indirect information about the soil subsurface properties, such as density, shear strength, and stratigraphy. Method: seismic refraction measures the travel time of seismic waves through the ground to estimate soil steepness and depth to bedrock. Electrical resistivity measures soil resistance to an electrical current, which provides information on soil composition, moisture content, and stratigraphy. Ground penetrating radar GPR uses radar waves to map subsurface structures, detecting interfaces between different soil layers, water tables, or buried objects. Applications: geophysical tests are commonly used for large-scale site investigations, where it is impractical to perform invasive methods. They are especially active for subsurface imaging, liquefaction studies, and depth to bedrock analysis. 3.1.3 Laboratory testing methods. After field samples are collected, laboratory testing is carried out to provide a detailed analysis of soil properties. Laboratory tests help engineers understand how the soil will behave under various load conditions and in different environments. 3.1.3.1 Grain size analysis. Purpose: grain size analysis determines the distribution of particle sizes in the soil sample. Method: the soil is sieved through a series of standardized screens or analyzed using a hydrometer for fine-grained soils. This test classifies the soil into categories such as gravel, sand, silt, or clay. Applications: grain size analysis is essential for identifying soil type and for determining parameters like permeability, compaction, and liquefaction. Susceptibility. 3.1.3.2 Atterberg limits, liquid and plastic limits. Purpose: the Atterberg limits measure the plasticity of fine-grained soils, such as clays and silts. Method: the liquid limit is determined by measuring the moisture content at which the soil changes from a liquid to a plastic state, while the plastic limit is the moisture content at which the soil can no longer be molded by hand. Applications: the Atterberg limits are used to assess soil behavior, shrinkage and swelling characteristics, and liquefaction potential. 3.1.3.3 Consolidation and compression tests. Purpose: these tests assess the compressibility and settlement of soil under load. Method: the soil sample is subjected to a series of vertical loads, and the resulting vertical strain is measured to determine the coefficient of consolidation and compressibility. Applications: consolidation tests are essential for predicting long-term settlement of foundations, embankments, and other structures. They are particularly important for soft, compressible soils such as clays. 3.1.3.4 Shear strength testing. Purpose: shear strength tests determine the shear resistance of soils, which is a key factor in the stability of slopes, foundations, and earth-retaining structures. Method: the triaxial test, direct shear test, and vane shear test are commonly used to assess shear strength in laboratory settings. Applications: shear strength testing is vital for analyzing slope stability, bearing capacity, and earthquake resistance. 3.1.4 Combining field and laboratory data. Combining both field investigation and laboratory testing data provides a comprehensive understanding of the subsurface conditions. The field data, such as soil stratigraphy and in situ test results, are supplemented by laboratory test results that measure specific soil properties. Engineers use this combined data to create soil profiles, estimate settlement potential, design foundations, and assess risk factors for de-erent construction. Scenarios. 3.1.5 Summary of Geotechnical Site Investigation Methods. Geotechnical site investigation methods involve a combination of preliminary surveys, field testing, and laboratory analysis to gather detailed information about soil and subsurface conditions. Field tests, such as borehole drilling, SPT, CPT, and vein shear tests, provide valuable real-time data, while laboratory tests, such as grain size analysis and shear strength testing, owe a deeper understanding of soil behavior under various loading conditions. By integrating both sets of data, engineers can make informed decisions that ensure the safety, stability, and long-term performance of geotechnical structures. Chapter 3: Site Characterization and Investigation. 3.2 Drilling and Sampling Techniques. Drilling and sampling are essential components of any geotechnical site investigation. These techniques are used to collect soil and rock samples from de-erent depths, which are then analyzed to determine the subsurface properties necessary for safe and efficient design and construction. The quality of the samples obtained, as well as the method of drilling, greatly influences the accuracy of the analysis and the overall success of the geotechnical investigation. This section discusses the various drilling and sampling techniques, highlighting the de-erent methods, types of equipment used, and their specific applications. 3.2.1 Drilling Techniques. Drilling is the process of creating boreholes in the ground to access subsurface materials. There are several drilling techniques, each suited for specific soil and rock conditions. The choice of drilling method depends on factors such as soil type, depth of sampling project, objectives, and the equipment available. 3.2.1.1 Rotary Drilling. Purpose. Rotary drilling is one of the most common methods used for drilling deep boreholes in both soft and hard formations. Method. A rotary drill bit is rotated at high speeds to cut through soil and rock. Water, air, or drilling mud is typically used as a flushing medium to remove cuttings and cool the bit. The cuttings are brought to the surface through the annular space between the drill pipe and the borehole wall. Applications. Rotary drilling is used in a variety of geotechnical investigations, including those in hard rock formations, deep borings for deep foundations, and when obtaining continuous core samples from solid rock formations. 3.2.1.2 Percussion Drilling, Cable Tool Drilling. Purpose. Percussion drilling, also known as cable tool drilling, is a traditional drilling technique used for shallow boreholes, particularly in soft to medium soils. Method. A heavy drilling bit is repeatedly lifted and dropped onto the ground to break through the material, allowing the drill bit to penetrate deeper. The technique relies on the force of repeated blows to break up the soil or rock. Applications. Percussion drilling is often used in shallow boreholes for obtaining soil samples in sand, clay, and loose gravel. It is particularly useful for relatively shallow and inexpensive investigations, but is not typically suitable for deep or hard rock drilling. 3.2.1.3 Hollowstem auger drilling. Purpose. Hollowstem auger drilling is a commonly used method in geotechnical investigations for soil sampling at shallow to intermediate depths. Method. A hollow metal auger is advanced into the ground by rotating it while simultaneously removing the material in the auger center. The hollow stem allows for continuous sample retrieval and the insertion of a liner or sampler inside the auger as it advances. Applications. This method is useful for obtaining undisturbed soil samples, especially in clays and silts. It is commonly used for shallow foundations, site characterization, and piezometer installation. 3.2.1.4 Continuous core drilling. Purpose. Continuous core drilling is employed for obtaining intact core samples from hard soils or rocks, providing an unbroken sample of subsurface material. Method. In this method, a cylindrical drill bit with a core barrel is used to obtain continuous core samples from deeper soil or rock layers. The drill bit cuts through the soil or rock, while the core barrel collects the material in a continuous form. Applications. Continuous core drilling is essential when it is necessary to obtain undisturbed samples of hard materials, such as rock formations and dense soils, for laboratory testing and engineering analysis. 3.2.1.5 Sonic drilling. Purpose. Sonic drilling is a high-frequency, low-amplitude method of drilling that is efficient for sampling hard soils and loose rock formations. Method. Sonic drilling uses high-frequency vibrations, sonic waves, generated by a vibrating drill head to create frictional heat that causes the soil to break apart. The vibrations allow for faster penetration of the drill into the soil or rock, and the drilled material is then collected in a liner. Applications. Sonic drilling is effective for both soft and hard formations, including cohesive soils, loose sands, and soft rocks. It is ideal for obtaining high quality continuous samples, even in difficult or challenging subsurface conditions. 3.2.2 Sampling techniques. Sampling is the process of collecting soil or rock samples from the borehole for laboratory analysis. The goal is to retrieve samples that accurately represent the in situ conditions of the subsurface materials, while maintaining the sample's integrity as much as possible. The most commonly used sampling techniques are described below. 3.2.2.1 Split barrel sampling, standard penetration test, SPE. Purpose. Split barrel sampling is a widely used method for collecting disturbed soil samples, especially in granular soils like sands and gravels, during the standard penetration test (SPT) method. A hollow, split-barrel sampler is driven into the soil by a hammer. The sampler collects soil as it is driven into the ground, and the number of blows required to advance the sampler a certain distance is recorded. The retrieved soil sample is considered disturbed, but can provide useful information about soil consistency and relative density. Applications. The SPT sample is used to assess the relative density of granular soils and to estimate shear strength for design purposes, particularly in shallow foundations and site investigations. 3.2.2.2 Shelby tube sampling, undisturbed sampling. Purpose. Shelby tube sampling is used to obtain undisturbed samples of cohesive soils, such as clays and silts, for laboratory testing of shear strength, compressibility, and consolidation. Method. A thin-walled steel tube is driven into the ground to collect a soil sample. The tube is carefully retrieved from the borehole, and the sample is preserved in the tube to minimize disturbance. The sample is kept intact and undisturbed during the extraction process. Applications. This technique is especially useful for obtaining undisturbed samples from fine-grained soils, including clays, silt, and soft soils, which are critical for understanding soil compressibility, consolidation, and shear strength. 3.2.2.3 Thin-walled tube sampling, undisturbed sampling. Purpose. Similar to the Shelby tube sampling, the thin-walled tube sampler is designed for undisturbed soil sampling, especially in cohesive or fine-grained soils. Method. A thin-walled steel tube is inserted into the ground using a light hammer or other techniques. The sample is retained in the tube, and the sample is carefully preserved to minimize disturbance. Applications. This technique is suitable for obtaining undisturbed samples from soft to medium clays and silts, often used for shear strength testing, consolidation testing, and plasticity testing. 3.2.2.4 Piston sampling, undisturbed sampling. Purpose. Piston sampling is another method for retrieving undisturbed samples from deeper soil layers, especially in sensitive or soft soils. Method. A piston sampler consists of a long steel tube fitted with a piston at the open end. The piston helps push the soil into the sampler without disturbing the sample. The sampler is driven into the ground, and the piston ensures the sample is retained intact. Applications. Piston sampling is used in sensitive clays, siltous soils, and low plasticity materials where it is important to minimize sample disturbance for accurate laboratory analysis, particularly in settlement and consolidation tests. 3.2.2.5 Core sampling, rock and hard soil sampling. Purpose. Core sampling is used to retrieve samples of hard rock or dense soils, which are difficult to sample with standard methods, like split barrel or Shelby tube. Samplers. Method. Core samples are typically retrieved using a core barrel, which cuts a cylindrical section of the material as it is drilled. The sample is removed from the barrel and analyzed for geological properties, such as mineral composition and strength. Applications. Core sampling is most commonly used in rock formations and dense soils for analyzing material properties such as compressive strength, fractures, and mineral composition. 3.2.2.6 Grab sampling. Purpose. Grab sampling is a simple technique used to obtain a quick, representative sample of soil from the borehole. Method. A small sample of soil is collected directly from the borehole using a hand auger or scoop, and the sample is placed in containers for transport and analysis. This method is less accurate than other sampling techniques, but can provide useful preliminary data. Applications. Grab sampling is often used for preliminary investigations, geotechnical screening, and site characterization when a quick sample is needed. 3.2.3 Considerations for drilling and sampling. Several factors must be considered when selecting drilling and sampling methods for a geotechnical investigation. Soil and rock type. Diorite drilling methods and samplers are suited for diorite. Soil and rock types. For example, rotary drilling is suitable for hard rocks, while auger drilling is better suited for soft soils. Depth of investigation. Deeper boreholes may require more advanced drilling methods such as rotary drilling, while shallow investigations can be done using simpler techniques such as percussion drilling or auger sampling. Sample integrity. Ensuring the integrity of undisturbed samples is critical, especially for cohesive soils, which can easily be disturbed by rough handling. Site conditions, accessibility, groundwater levels, and the presence of obstacles, like utilities or structures, must be considered when planning the drilling and sampling program. 3.2.4 Summary of drilling and sampling techniques. Drilling and sampling are essential for obtaining subsurface data and understanding soil and rock conditions at a site. Common drilling methods include rotary, percussion, and auger drilling, each suited for specific soil and rock types. Sampling techniques such as split barrel, Shelby tube, piston, and core sampling help obtain soil and rock samples for laboratory analysis. These techniques, when combined, provide engineers with the data needed to assess the soil properties, guide foundation design, and identify potential construction challenges. Chapter 3. Site Characterization and Investigation. 3.3 Geophysical Survey Methods. Geophysical survey methods are non-invasive techniques used to assess subsurface conditions without the need for extensive drilling or excavation. These methods provide valuable information on the physical properties of the soil and rock layers beneath the ground surface, offering insights into their composition, structure, and behavior. Geophysical surveys are often used in conjunction with traditional drilling and sampling techniques to provide a more comprehensive site characterization. This section discusses the various geophysical survey methods, highlighting their principles, types, applications, and limitations. 3.3.1 Overview of Geophysical Survey Methods. Geophysical methods utilize the principles of physics to measure subsurface properties, such as density, electrical resistivity, seismic velocity, and magnetic properties. These properties are influenced by the type and condition of the materials below the surface, allowing engineers and geophysicists to infer subsurface conditions. The main types of geophysical methods include seismic methods, electrical resistivity methods, magnetic methods, ground-penetrating radar (GPR), electromagnetic methods, gravity surveys. Each of these methods provides different types of data, which can be used to characterize the subsurface in terms of soil and rock stratigraphy, groundwater conditions, and potential hazards. 3.3.2 Seismic methods. Seismic methods are among the most commonly used geophysical techniques in geotechnical investigations. They are based on the measurement of seismic waves that travel through the ground and reflect different subsurface layers. By analyzing the travel time and velocity of these waves, the properties of the subsurface can be determined. 3.3.2.1 Seismic refraction. Purpose: seismic refraction is used to determine the depth to bedrock, the velocity of seismic waves in different layers, and the presence of soil or rock anomalies. Method: a source of seismic waves, such as a small explosive charge or a hammer, strike on the ground, generates waves that travel through the soil and rock. The waves are refracted, bent, at interfaces between layers of different seismic velocities. Seismic sensors, geophones, placed along the surface measure the time it takes for the waves to return. Applications: this method is commonly used to identify the depth to bedrock, locate water tables, and assess soil steepness. It is particularly useful for shallow to intermediate depths in areas where drilling is expensive or impractical. 3.3.2.2 Seismic reflection. Purpose: seismic reflection involves the measurement of seismic waves that are reflected off subsurface layers, similar to how sound waves reflect off surfaces. Method: a controlled source generates seismic waves, which travel through the ground and reflect layer interfaces. These reflected waves are detected by sensors and analyzed to determine the subsurface structure. Applications: seismic reflection is used for deep geotechnical investigations, such as deep foundation design, geotechnical mapping, and subsurface imaging for complex sites, like those with multiple soil and rock layers. This method is effective for large-scale site surveys and understanding geological formations. 3.3.2.3 Microtremor and ambient noise measurements. Purpose: these methods use natural vibrations or noise generated by environmental factors, e.g., wind, IC, to evaluate subsurface conditions. Method: sensors placed at various locations on the surface measure the natural seismic noise. The noise data are processed to infer information about the subsurface layers. Applications: microtremor measurements are used for site-specific seismic hazard analysis, soil structure interaction, and assessment of soil properties in areas with high seismic activity. 3.3.3 Electrical resistivity methods. Electrical resistivity methods measure the ability of the ground to conduct electrical current. Diorite subsurface materials have diorite resistivities, with clays having low resistivity and sands, gravels, and rocks having higher resistivity. These diorites help identify layers of soil and rock, the depth to the water table, and the presence of potential contaminants. 3.3.3.1 Electrical resistivity tomography, ERT. Purpose: ERT is used to map the vertical and horizontal distribution of resistivity in the subsurface, providing a clear image of soil layers, groundwater flow, and contamination zones. Method: electrodes are placed along the surface of the ground and an electrical current is injected into the soil. The voltage difference between electrodes is measured, and the resistivity of the material is calculated. The data is then processed to generate a resistivity profile or 2D/3D resistivity map of the subsurface. Applications: ERT is used for subsurface imaging, groundwater monitoring, contaminant detection, and geotechnical site characterization. It is particularly useful in environmental engineering and hydrogeology. 3.3.3.2 Induced polarization, IP. Purpose: the induced polarization method measures the delay in the flow of electric current through the ground after a current pulse is applied. It is useful for detecting clay-rich soils, fractured rocks, and groundwater flow. Method: similar to ERT, the IP method uses electrodes to inject an electrical current into the ground. The voltage is monitored for a delay or polarization, EECT, that occurs due to the electrochemical properties of certain subsurface materials. Applications: IP is effective in detecting clay deposits, mineral exploration, and assessing soil contamination. 3.3.4 Magnetic methods. Magnetic surveys measure variations in the Earth's magnetic field caused by the presence of magnetic minerals in subsurface materials, such as iron-rich rocks. These surveys help detect anomalies in the magnetic field, which may indicate the presence of buried structures or geological features. 3.3.4.1 Magnetic Field Mapping. Purpose: magnetic surveys are used to detect subsurface anomalies such as faults, fractures, and mineral deposits, as well as man-made features like pipes or tanks. Method: a magnetometer is used to measure the strength and variations in the Earth's magnetic field. The data is then processed to map anomalies in the subsurface. Applications: magnetic surveys are commonly used in archaeology, mineral exploration, and site investigations for detecting underground utilities, buried structures, and geological features such as faults or volcanic intrusions. 3.3.5 Ground Penetrating Radar (GPR). Ground Penetrating Radar (GPR) is a non-destructive testing method that uses high-frequency radio waves to image the subsurface. It provides real-time data and is particularly useful for shallow investigations. 3.3.5.1 GPR Survey. Purpose: GPR is used to detect subsurface features such as soil layers, water tables, utilities, voids, and buried objects, as well as to map the depth to bedrock or interface between de-erent soil layers. Method: a GPR system emits high-frequency electromagnetic waves that penetrate the ground and reflect various subsurface interfaces. The reflected signals are recorded by a receiver and analyzed to create images of the subsurface. Applications: GPR is widely used in shallow site investigations, such as for detecting utilities, voids, delineating soil layers, and assessing groundwater conditions. It is commonly used in civil engineering, construction, and environmental investigations. 3.3.6 Electromagnetic Methods. Electromagnetic (EM) methods measure variations in the ground's ability to conduct an electrical current and are commonly used to detect the presence of water or contamination in the subsurface. 3.3.6.1 Frequency Domain Electromagnetic (FDM) Survey. Purpose: FDM is used to map the conductivity of the subsurface and is useful for detecting water-saturated zones, saltwater intrusion, or contaminant plumes. Method: an EM field is induced into the ground, and the resulting electromagnetic response is measured by sensors. The data is processed to identify variations in the conductivity of the ground at de-erent depths. Applications: FDM is widely used in environmental investigations, groundwater monitoring, and contaminant detection. 3.3.7 Gravity Surveys. Gravity surveys measure variations in the Earth's gravitational field caused by changes in subsurface density. This method can identify subsurface features such as faults, cavities, and dense rock layers. 3.3.7.1 Gravity Mapping. Purpose: gravity surveys are used to detect anomalies in the Earth's gravitational field, which can reveal the presence of mineral deposits, subsurface voids, and geological structures. Method: a gravimeter is used to measure the gravitational pull at various locations. On the surface, the variations in gravitational force are analyzed to detect anomalies. In the subsurface, applications: gravity surveys are primarily used in mineral exploration, geological mapping, and hydrocarbon exploration. 3.3.8 Summary of Geophysical Survey Methods. Geophysical survey methods provide valuable insights into subsurface conditions, complementing traditional drilling and sampling techniques. Each method offers distinct advantages depending on the specific site conditions and investigation objectives. Seismic methods are ideal for mapping the depth to bedrock and assessing soil steepness, while electrical resistivity and GPR are well suited for environmental investigations and identifying underground utilities. Magnetic and gravity methods are useful for detecting geological anomalies, and electromagnetic methods are particularly effective for assessing water or contamination in the subsurface. By integrating these techniques, geotechnical engineers can obtain a more comprehensive understanding of the subsurface, aiding in design, risk assessment, and decision-making for construction projects. Chapter 3: Site Characterization and Investigation. 3.4 Laboratory Testing of Soil Samples. Laboratory testing of soil samples is an essential part of geotechnical site investigations. These tests are conducted to determine the physical, chemical, and mechanical properties of soil and rock materials, which are critical for designing safe and effective foundation systems, retaining structures, and other geotechnical features. Laboratory tests provide data on soil strength, compressibility, permeability, and other characteristics that cannot be directly observed in the field. This section outlines the primary laboratory tests conducted on soil samples, describing their methods, applications, and the types of information they provide. 3.4.1 Overview of laboratory testing. Laboratory tests are performed on soil samples that have been retrieved from the site using drilling and sampling methods such as Shelby tube sampling, split barrel sampling, or core sampling. These tests are typically classified into two main categories. Index tests provide basic information about the soil's composition and classification. Engineering tests provide data on the soil's mechanical and physical properties, such as strength, compressibility, and permeability. The following subsections cover the major types of laboratory tests commonly used in geotechnical engineering. 3.4.2 Index tests. Index tests are used to determine the classification of soil and provide basic information about its composition, texture, and consistency. These tests are quick, relatively simple, and inexpensive to perform, making them a vital part of initial soil investigations. 3.4.2.1 Grain Size Analysis, Sieve Analysis and Hydrometer Method. Purpose: grain size analysis is used to determine the distribution of particle sizes in a soil sample. Method: sieve analysis is used for coarse-grained soils, sand and gravel, by passing the soil through a series of sieves with different mesh sizes and weighing them. Amount of material retained on each sieve. The hydrometer method is used for fine-grained soils, silt and clay to measure the particle size distribution in suspension, using the rate at which particles settle in a liquid. Applications: grain size analysis helps classify soils into categories like clays, silts, and sands and is important for evaluating soil behavior, permeability, and suitability for construction. 3.4.2.2 Atterberg Limits. Purpose: the Atterberg limits define the boundaries between different states of consistency for fine-grained soils, clays, and silts, based on their moisture content. Method: the two main limits measured are liquid limit, the moisture content at which the soil transitions from a liquid state to a plastic state. Plastic limit, the moisture content at which the soil transitions from a plastic state to a semi-solid state. Shrinkage limit, the moisture content at which further loss of moisture does not result in any decrease in soil volume. Applications: these limits are used to classify fine-grained soils, assess their plasticity, and predict their behavior under different moisture conditions. The Plasticity Index, PI, calculated as LLPL, helps indicate the soil shrink-swell potential. 3.4.2.3 Specific gravity of soil solids. Purpose: specific gravity is the ratio of the density of soil solids to the density of water and provides insight into the mineral composition of the soil. Method: the specific gravity is typically measured by the pycnometer method or the density bottle method. Applications: this test is useful in determining the soil's compaction characteristics, and its value is used in calculations for compaction control, void ratio, and porosity. 3.4.3 Engineering tests. Engineering tests are conducted to determine the mechanical and physical properties of soil, which influence its performance in various engineering applications such as foundation design, slope stability, and soil reinforcement. 3.4.3.1 Compaction Test, Proctor Test. Purpose: the compaction test determines the relationship between the moisture content and the dry density of the soil, which helps in understanding its compactability. Method: in the standard Proctor test, a soil sample is compacted into a mold at various moisture contents using a standard compactive ort. The dry density is then measured for each moisture content, and the results are plotted to obtain the optimum moisture content, OMC, and maximum dry density, MDD. Applications. The results of this test are used in earthworks and embankment, designed to ensure that the soil is compacted to an appropriate density for construction and to prevent excessive settlement. 3.4.3.2 Unconfined Compressive Strength UCS Test. Purpose. The UCS test is used to measure the strength of cohesive soils, primarily clays and silts, by determining the maximum axial stress that a soil specimen can withstand when subjected to unconfined compression. Method. A cylindrical soil sample is loaded axially until failure occurs. The maximum stress at failure is recorded as the unconfined compressive strength. Applications. UCS is used to assess the shear strength of soft clays and is commonly applied in foundation design, slope stability analysis, and shallow excavation. 3.4.3.3 Triaxial Shear Test. Purpose. The triaxial shear test measures the shear strength of soil under controlled conditions, simulating the stress and strain behavior that occurs in the field. Method. A cylindrical soil specimen is placed inside a chamber and pressure is applied on all sides, confining pressure, while a vertical load is applied to induce shearing. The test can be performed under drained or undrained conditions, and the results provide the shear strength parameters, cohesion, and angle of internal friction. Applications. The triaxial test is essential for foundation design, earth retaining structures, slope stability analysis, and seismic analysis. 3.4.3.4 Direct Shear Test. Purpose. The direct shear test measures the shear strength of soil by determining the shear stress at which a soil sample fails under controlled conditions. Method. A soil specimen is placed in a shear box, and a normal load is applied to the sample. The box is then sheared at a constant rate, and the shear force is measured. Applications. This test is commonly used to determine shear strength parameters, particularly in granular soils, such as sands and gravels, and is often applied in shallow foundation design and slope stability analysis. 3.4.3.5 Consolidation Test. Purpose. The consolidation test measures the settlement characteristics of fine-grained soils, clays, and silts under compressive loads over time, simulating the EX of external loads, such as those from buildings or embankments. Method. A soil sample is placed in a consolidation cell where a vertical load is applied to simulate field conditions. The decrease in sample thickness over time is measured to determine the coefficient of consolidation, CV, and the compression index, CC. Applications. This test is crucial for assessing the settlement behavior of fine-grained grain soils and predicting long-term settlement under sustained loads, which is critical for foundation design. 3.4.3.6 Permeability Test, Constant Head and Falling Head Methods. Purpose: the permeability test measures the rate at which water flows through a soil sample, which is essential for assessing drainage properties and groundwater flow. Method: constant head method is used for coarse-grained soils, sand and gravel, where water is allowed to flow through the sample at a constant head, and the flow rate is measured. Falling head method is used for fine-grained soils, clays and silts, where water flows through the sample, and the time it takes for the water level to fall a certain distance is recorded. Applications: permeability data is essential for evaluating groundwater flow, drainage systems, and foundation design in areas with high water tables or expansive soils. 3.4.3.7 California Bearing Ratio CBR Test. Purpose: the CBR test measures the resistance of soil to penetration by a standardized piston under controlled moisture and density conditions. Method: a piston is driven into a compacted soil sample under a specified load, and the resistance is measured at various penetration depths. The ratio of the applied load to a standard load is recorded as the CBR value. Applications: the CBR test is widely used for pavement design, particularly in highway and road construction, as it helps assess the bearing capacity of granular soils. 3.4.4 Summary of laboratory testing of soil samples. Laboratory testing of soil samples is crucial for obtaining detailed information about the soil's physical and mechanical properties, which are necessary for geotechnical design and analysis. Index tests, such as grain size analysis and Atterberg limits, provide basic classification data, while engineering tests, including compaction tests, shear strength tests, and consolidation tests, provide in-depth data on the soil's load-bearing and deformation characteristics. These tests are vital for understanding the behavior of soils under various loading and environmental conditions, ensuring that structures are built on stable, reliable foundations. Chapter 3: Site Characterization and Investigation. 3.5 Site Data Interpretation and Analysis. The process of site data interpretation and analysis involves evaluating the results obtained from geotechnical investigations, including field and laboratory tests, to make informed decisions about soil behavior, site conditions, and the potential impact on foundation design, construction, and site development. Proper interpretation and analysis are essential for understanding the subsurface conditions, identifying potential geotechnical hazards, and making design recommendations that ensure the safety and stability of the proposed structures. This section outlines the key concepts, methods, and approaches for interpreting and analyzing geotechnical data, focusing on the integration of field data, laboratory results, and geophysical information to draw meaningful conclusions for engineering design. 3.5.1 Overview of Site Data Interpretation and Analysis. Site data interpretation begins with the analysis of geotechnical data from different sources, including field investigation results, e.g., soil borings, geophysical surveys, and in situ tests, laboratory test results, e.g., grain size analysis, Atterberg limits, and strength tests, geophysical data, e.g., seismic profiles, electrical resistivity data, site-specific conditions, e.g., groundwater levels, soil stratigraphy, and existing structures. These data must be integrated and analyzed to form a comprehensive understanding of the site's geotechnical characteristics. This process may involve several stages of analysis, such as data quality control, interpretation, modeling, and the development of design parameters for the project. 3.5.2 Data Quality Control and Validation. Before proceeding with any interpretation or analysis, it is critical to ensure the quality and consistency of the data collected from field and laboratory tests. This involves several steps. Review of field and laboratory procedures. Ensure that all tests were performed following standard procedures and protocols to avoid errors or inconsistencies. Consistency checks. Verify that the data from different tests, e.g., boring logs, laboratory tests, and in situ tests, are consistent with each other. For example, the results from a cone penetration test, CPT, should align with soil classification data from borehole sampling. Identification of outliers. Detect any anomalous or inconsistent data points and investigate their cause. Outliers could indicate errors during data collection or unusual site conditions that need special consideration. Once data quality control measures are completed, the next step is to interpret the data accurately and use it to develop a comprehensive understanding of the site. 3.5.3 Soil stratigraphy and subsurface profiles. The analysis of soil stratigraphy is crucial for understanding the vertical and lateral distribution of different soil layers beneath the ground surface. This information is used to create a subsurface profile or soil profile that represents the distribution of soil types, strength, and other geotechnical parameters at various depths. Key elements in the interpretation of soil stratigraphy include soil layer identification, based on the results from borehole sampling, CPT, and field observations. Identify the distinct soil layers, their boundaries, and transitions. Each layer is typically classified based on its composition, e.g., sand, clay, silt, consistency, e.g., soft, variety, and other characteristics, e.g., plasticity. Depth of soil layers. Determine the depth of each soil layer and the depth to bedrock or hard strata. This is critical for foundation design and understanding. Settlement behavior. Lateral variability. If multiple boreholes or geophysical surveys are available, analyze how soil conditions vary laterally across the site, which is essential for large-scale projects. Creating a subsurface profile allows engineers to visualize the distribution of soil properties across different depths, aiding in the determination of suitable foundation depths. Potential for settlement and expected soil behavior under loading. 3.5.4 Groundwater conditions and hydrological analysis. Groundwater conditions play a significant role in geotechnical site analysis. The water table, groundwater flow, and soil-water interaction must be carefully assessed and integrated into the data analysis process. Key considerations for interpreting groundwater data include location of the water table. Determine the depth of the water table based on borehole observations, piezometer data, and any site-specific historical data on groundwater levels. Seasonal fluctuations. Groundwater levels can fluctuate due to seasonal changes, rainfall, and nearby construction activities. It is important to assess long-term trends in water levels to estimate the worst-case scenario for construction. Groundwater flow. Analyze groundwater flow patterns using hydraulic conductivity tests, piezometer data, and seepage analysis to understand the rate and direction of groundwater movement beneath the site. This is essential for evaluating the risk of piping, erosion, or hydraulic fracturing during construction. Incorporating groundwater conditions into the overall interpretation of site data allows for the design of appropriate dewatering systems, if necessary, the assessment of foundation stability under fluctuating water levels, and the identification of potential geotechnical hazards like uplift pressure or settlement due to water ingress. 3.5.5 Geotechnical parameters and design criteria. Based on the interpreted site data, engineers can derive the necessary geotechnical design parameters that influence foundation design and other engineering decisions. Some of the most important parameters derived from site data interpretation include soil strength parameters. These include cohesion, C, angle of internal friction, phi, and shear strength parameters derived from tests like the triaxial shear test, direct shear test, and unconfined compressive strength test. These parameters are critical for assessing the bearing capacity of the soil and designing foundations. Settlement parameters. Data from consolidation tests and field observations are used to assess potential settlement under loading. These parameters help determine the expected total settlement and differential settlement that may occur during construction and over time. Permeability parameters. The coefficient of permeability, K, is critical for evaluating drainage, seepage, and water flow through the soil, influencing the design of foundations, pavements, and retaining structures. By calculating and validating these design parameters, engineers can assess whether the site is suitable for the proposed construction and recommend specific measures to mitigate risks related to soil strength, settlement, and water-related issues. 3.5.6 Numerical Modeling and Advanced Analysis. In many cases, site data interpretation involves more advanced analysis techniques, including numerical modeling, to simulate complex geotechnical behavior. Finite element analysis, FEA, finite difference method, FDM, and other advanced modeling techniques are used to simulate soil behavior under varying conditions, such as loading, moisture changes, and excavation. Key aspects of numerical modeling in geotechnical site analysis include model calibration. Use the available site data, including field test results, laboratory test data, and geophysical survey data, to calibrate the model and ensure that it accurately reflects the soil behavior at the site. Simulation of loading conditions. Apply realistic loading conditions to the model, including dead loads, live loads, seismic forces, and other relevant stresses to analyze the potential settlement, soil deformation, and structural stability. Long-term behavior. Model the long-term behavior of soils under varying conditions, such as changes in groundwater level, seasonal moisture content, or construction activities. Advanced numerical modeling techniques can provide insights into complex geotechnical behavior, particularly for large or challenging sites, helping engineers optimize their design and minimize risks. 3.5.7 Interpretation of geotechnical risks. Finally, interpreting site data includes identifying potential geotechnical risks that could impact construction and long-term performance. Some common risks include liquefaction risk. Analyze soil susceptibility to liquefaction during seismic events, particularly for loose, saturated sandy soils. Slope stability. Assess the potential for slope failure or landslides based on soil properties and site conditions. Expansive soils. Identify the presence of shrink-swell soils, which can cause significant foundation movement due to changes in moisture content. By identifying and quantifying geotechnical risks, engineers can propose mitigation measures such as soil stabilization, foundation deepening, drainage systems, or seismic retrofitting to reduce the impact of these risks on construction and long-term performance. 3.5.8 Summary of Site Data Interpretation and Analysis. Site data interpretation and analysis is a critical step in the geotechnical engineering process. It involves reviewing, integrating, and analyzing data from various sources to create a comprehensive understanding of the site's subsurface conditions, soil behavior, and potential risks. Through careful data interpretation, engineers can derive essential design parameters for foundations, evaluate geotechnical risks, and make informed decisions on how to proceed with construction. Advanced analysis tools, such as numerical modeling and geotechnical risk analysis, further enhance the accuracy and reliability of the interpretation, ensuring that the proposed design is safe, efficient, and sustainable. We hope you found the content informative and valuable. The link to part 2 of this video will be embedded in the description below, so be sure to check it out. If you enjoyed the video, please click like and share it with others. And if you haven't subscribed to our channel yet, make sure to hit the subscribe button now so you don't miss out on future content.